The first thing that strikes you in a reef dense with motion is not the predators that announce themselves through size or speed, but the ones that seem to have opted out of the race entirely, choosing instead to survive through stillness so complete that it bends perception. A seahorse does not enter the scene like a hunter in any traditional sense, because nothing about its posture, proportions, or behavior signals danger to the surrounding microfauna drifting through the water column. Its body is upright, almost botanical in stance, the tail wrapped around a strand of seagrass or a coral finger, as if anchoring against boredom rather than current. And its face ends in a narrow snout that looks less like a weapon and more like an accident of evolution, an oddly bent tube that appears ill-suited for anything dramatic. In a reef environment shaped by jaws, spines, bursts of speed, and overt aggression, the seahorse seems like a mistake that somehow survived, an animal built for decoration rather than dominance, and that false assumption is precisely what allows it to operate as one of the most precise ambush predators in shallow marine ecosystems. Watch closely, and the illusion of harmlessness begins to fracture, not through sudden movement, but through attention. The eyes of a seahorse do not behave like the eyes of most fish, which tend to move in coordination or lock together when tracking a target. Instead, each eye operates independently, swiveling in different directions with unsettling autonomy, creating a continuous panoramic surveillance of the surrounding space. One eye may track the slow descent of plankton drifting on the current, while the other monitors a copepod navigating the reef edge, and neither movement interferes with the other. This split attention is not a novelty or a curiosity. It is a direct response to the seahorse's ecological constraints. Lacking the streamlined body and muscular propulsion required for pursuit, the seahorse compensates by maximizing detection, effectively turning its head into a biological radar array that samples the environment in overlapping arcs. In a habitat where prey items are small, transparent, and fleeting, the ability to monitor multiple vectors at once is not a luxury but a necessity, allowing the animal to detect opportunity without repositioning its body or breaking camouflage. That camouflage is not passive coloration alone, but a complex interplay between morphology, texture, and behavior. Seahorses are often covered in bony plates rather than flexible scales, giving them a rigid, angular surface that disrupts their outline when viewed against coral rubble or branching algae. Many species develop filamentous growths or skin appendages that mimic the fronds of seagrass or the knobby textures of sponges, and their tendency to sway gently with the movement of the water further reinforces the illusion that they are part of the reef's static architecture rather than an organism with intent. This behavioral mimicry is as important as visual resemblance, because predators and prey alike are tuned to detect deviations in motion more than color, and the seahorse's refusal to move decisively until the exact moment of attack keeps it below the threshold of attention for most small animals sharing the space. The prey drifting into this ambush zone are not careless, nor are they slow by default. Copepods, amphipods, larval crustaceans, and tiny shrimp species have evolved rapid escape responses, often powered by sudden tail flicks or explosive jumps that can propel them many body lengths away in a fraction of a second. In open water, speed is survival, and even within the reef, reaction time often determines whether an animal becomes food or lives to reproduce. The seahorse does not challenge this system by trying to outrun its prey, because that would be futile. Instead, it bypasses the contest entirely by exploiting physics rather than muscle, relying on a feeding mechanism so fast and so localized that the prey never experiences a chase at all. The attack begins with stillness so complete that it is difficult to tell when the decision has been made. The seahorse's eyes lock onto a target, both now converging on the same point in space, and the angle of its head shifts almost imperceptibly to align the snout with the prey's trajectory. There is no dramatic coil of the body, no preparatory twitch that would telegraph intent. Then, in a time span measured in thousandths of a second, the seahorse triggers one of the fastest suction-feeding events in the animal kingdom. The hyoid apparatus inside the head snaps downward, expanding the volume of the oral cavity almost instantaneously, and the resulting pressure drop creates a localized vacuum that pulls water and everything suspended in it straight into the snout. To the prey, there is no visible mouth lunging forward, no closing jaws, no sense of being chased or grabbed. Instead, the surrounding water itself accelerates toward a point that did not exist a moment before, and the animal is carried along helplessly, erased not by force, but by fluid dynamics. This method of feeding is often described as suction, but that word fails to capture the violence of the event at such a small scale. The flow speeds generated at the entrance of the snout are sufficient to overwhelm the escape responses of prey that are otherwise capable of impressive bursts of acceleration, because reaction time becomes irrelevant when the attack is completed before the nervous system can process the threat. By the time the prey's sensory structures detect the change in pressure or flow direction, it is already inside the feeding tube, where backward-facing structures and rapid closure prevent any chance of escape. The seahorse does not need to overpower its prey because it never gives the prey an opportunity to resist, turning the water itself into the delivery mechanism of death. What makes this strategy particularly effective is its precision. Unlike larger suction feeders that engulf broad volumes of water, the seahorse's strike is highly targeted, minimizing wasted energy and reducing the risk of alerting other potential prey in the vicinity. This precision is critical in an environment where energy budgets are tight and feeding opportunities are unpredictable. Seahorses lack a true stomach, meaning that food passes through their digestive system relatively quickly, and they must feed frequently to meet their metabolic needs. A hunting strategy that relies on long pursuits or repeated failed strikes would be unsustainable, but the combination of constant visual monitoring and near-guaranteed capture success allows the seahorse to maintain energy balance despite its slow, seemingly inefficient lifestyle. This approach to predation also influences the seahorse's relationship with its environment in subtle ways. By focusing on small, abundant prey, rather than competing for larger, more contested food sources, seahorses occupy a niche that reduces direct competition with faster, more aggressive reef fish. Their feeding pressure helps regulate populations of tiny crustaceans and planktonic organisms, contributing to the balance of the reef's microfaunal community, even though their presence is rarely acknowledged in discussions of reef dynamics dominated by larger predators. In this sense, the seahorse functions as a quiet stabilizer, exerting influence through countless invisible interactions rather than dramatic displays of dominance. The independent movement of the eyes, which initially appears almost comical, is tightly integrated with this feeding strategy. By scanning continuously without repositioning the body, the seahorse reduces the need for movement that could compromise camouflage, while also increasing the likelihood of detecting prey drifting in from unpredictable directions. This dual focus allows the animal to operate effectively in complex flow environments where currents shift around coral heads and seagrass blades, carrying prey along non-linear paths that would be difficult to track with a single fixed line of sight. The result is a predator that appears passive, but is in fact engaged in constant, high-resolution monitoring of its surroundings, ready to exploit the precise moment when physics can be turned into a weapon. There is a quiet irony in the fact that such an advanced hunting system belongs to an animal so often dismissed as fragile or ornamental. Seahorses are frequently portrayed as symbols of delicacy, their slow movements and unusual appearance lending themselves to narratives of vulnerability rather than competence. Yet beneath that aesthetic lies a suite of adaptations honed for efficiency rather than spectacle, proving that success in evolution does not always favor the fastest or the strongest, but often the most precise. The seahorse does not chase because it does not need to, does not intimidate because it does not compete in that arena, and does not advertise its lethality because concealment is its greatest ally. In the broader context of predator strategies, the seahorse represents a different solution to the problem of survival, one that prioritizes detection, timing, and mechanical advantage over speed and endurance. Its hunting method underscores a fundamental truth about ecological systems: that performance cannot be judged by appearances alone, and that some of the most effective predators are those that remove themselves from the obvious contests altogether. By mastering the art of seeing without being seen, and by weaponizing the physical properties of water itself, the seahorse demonstrates that in the reef's crowded battlefield, precision can outperform power, and patience can outcompete speed. This is why it belongs at the beginning of this exploration, not as a curiosity, but as a reminder that danger in the ocean often arrives not with a chase, but with silence, alignment, and a sudden collapse of the space you thought was safe. Long before a great white shark ever becomes visible in coastal water, before its silhouette resolves into something recognizable against the shifting light from the surface, the encounter has already begun on a level that has nothing to do with vision, speed, or teeth. The ocean at this scale is not an empty blue void, but a dense electrical landscape, threaded with faint signals generated by every living body that moves, breathes, or contracts a muscle. And the great white navigates this invisible terrain with a sensory system that turns proximity itself into vulnerability. In murky surf zones, where suspended sand erases contrast and sunlight fractures into useless glare, the shark does not hunt blind, because blindness in this environment would be a death sentence for any large predator dependent on accuracy. Instead, it hunts by reading the electric fingerprints of life, sensing the presence of prey through signals so weak they would seem irrelevant anywhere outside seawater, yet here become as informative as a trail of light. The foundation of this ability lies in a network of sensory organs embedded across the shark's snout and head, known as the ampullae of Lorenzini, which appear externally as tiny pores, but function internally as highly sensitive electroreceptors tuned to detect minute voltage differences in the surrounding water. These structures are filled with a conductive gel that transmits external electrical changes to sensory cells, capable of responding to electrical gradients generated by muscle contractions, nerve impulses, and even the rhythmic beating of a heart. In practical terms, this means that any animal with active muscles becomes a source of detectable information, broadcasting its presence not through sound or sight, but through the unavoidable physics of living tissue. A struggling fish, a wounded seal, or a body simply maintaining posture in moving water generates a pattern of electrical signals that the shark can interpret with remarkable precision once it is close enough for those signals to stand out against the background noise of the sea. This sense does not replace vision or smell, but complements them in a layered hunting strategy that reflects the complexity of coastal ecosystems where great white sharks often operate. At longer ranges, olfactory cues dominate, allowing sharks to follow scent trails carried by currents over considerable distances. But smell alone cannot provide exact location or orientation, especially in turbulent water where currents twist and break apart chemical plumes. Vision becomes more useful as distance closes, yet visibility in nearshore environments is notoriously unreliable, shaped by sediment, plankton blooms, surface glare, and shifting light angles that distort shapes and sizes. Electroreception fills the final gap, operating most effectively at close range, where it provides precise, real-time information about the position and movement of prey, even when visual confirmation is incomplete or misleading. This is why great white sharks do not need a clear view to initiate an attack. They only require enough sensory overlap to confirm that what they are approaching is alive, sizable, and within striking distance. From the perspective of the prey, this layered detection system is deeply unsettling because it removes many of the traditional defenses animals rely on to avoid predation. Remaining still, blending into the background, or choosing low visibility conditions may reduce the effectiveness of visual predators. But these strategies do nothing to suppress the electrical activity generated by a living body. Even a motionless seal floating at the surface produces detectable signals through muscle tone adjustments and involuntary physiological processes, turning its own metabolism into a beacon once a shark enters the critical detection zone. This zone is not vast, but it does not need to be, because by the time electroreception becomes the dominant sense guiding the shark, the distance between predator and prey has already collapsed to a range where reaction time matters more than awareness. The great white's hunting style reflects this reality, relying on stealth and timing rather than prolonged pursuit, particularly when targeting fast, agile prey such as seals and sea lions. Rather than chasing from afar, which would give prey ample warning and expend valuable energy, the shark approaches from below or behind, using depth and angle to remain hidden until the final moments. In this phase, vision and electroreception work together, with the shark refining its trajectory based on subtle shifts in the electrical field produced by the prey's movements. The closer the shark gets, the clearer this electrical image becomes, allowing it to adjust its approach even if visibility is compromised by turbulence or low light. When the strike occurs, it is not a desperate lunge but a calculated interception, timed to exploit the prey's limited ability to detect or respond to a threat that has already entered its personal space. What makes this sensory system particularly effective is its resistance to deception. While some prey species evolve camouflage patterns or behavioral strategies that reduce visual detectability, there is no biological equivalent of turning off electricity without ceasing to live. Muscles must contract to maintain posture, nerves must fire to coordinate movement, and hearts must beat to circulate oxygen, all of which generate electrical signals that propagate through seawater. Even attempts to minimize movement cannot eliminate these signals entirely, meaning that once a great white is within electroreceptive range, concealment becomes nearly impossible. This is why encounters often seem sudden and inexplicable to human observers, who rely heavily on vision and assume that what cannot be seen cannot pose an immediate threat, underestimating the extent to which the shark has been tracking them through other means. The effectiveness of electroreception also shapes how great white sharks interact with unfamiliar objects, including humans, whose electrical signatures differ from those of typical prey. A human in the water generates electrical patterns through muscle activity and heartbeats that are detectable but unfamiliar, and this mismatch likely contributes to investigatory behavior rather than immediate predatory commitment in many encounters. The shark is able to detect presence and approximate location without fully resolving identity, which helps explain why visual confirmation often precedes a test bite rather than a full predatory sequence. This does not make the sense benign or comforting, but it underscores its role as a detection tool rather than a kill switch, providing information that must still be interpreted within the broader context of the shark's sensory input and ecological experience. From an evolutionary perspective, electroreception represents an elegant solution to the challenges posed by aquatic environments, where light behaves unpredictably and sound travels too broadly to offer precise localization at close range. By exploiting the conductive properties of seawater, sharks have developed a sensory channel that functions independently of external conditions such as turbidity or lighting, giving them a consistent advantage in the final moments of an encounter. This advantage is particularly pronounced for a large ambush predator like the great white, which cannot afford repeated failed attacks due to the energetic cost of acceleration and the risk of injury from struggling prey. Precision is not optional, it is a prerequisite for survival at this scale. The unsettling implication of this system is that awareness does not equal safety. A prey animal may detect the presence of a shark visually at the same moment the shark has already locked onto its electrical signal, collapsing the window for escape into a fraction of a second. By the time electroreception becomes decisive, the encounter has already moved past the stage where distance offers protection and the only remaining variable is timing. This is why great white attacks are often described as explosive and sudden, not because the shark moves faster than expected, but because the critical detection phase occurs at a range where human perception is already too slow to matter. In the broader ecology of the ocean, this sensory ability reinforces the great white's role as a regulator rather than a mere consumer. By preferentially targeting weak, injured, or distracted prey, whose electrical signals may differ subtly from those of healthy individuals, sharks contribute to population health through selective pressure, removing individuals less capable of avoiding predation. This effect ripples through the ecosystem, influencing prey behavior, distribution, and even energy flow, demonstrating that the shark's impact extends far beyond the dramatic moment of the strike. The idea of a sixth sense is often framed in popular culture as something mystical or exaggerated, but in the case of the great white shark, it is grounded firmly in physics and physiology, emerging from the unavoidable realities of living tissue interacting with conductive seawater. There is nothing supernatural about it, yet its consequences are deeply unsettling for any creature accustomed to thinking of vision as the primary gateway to awareness. In this underwater world, eyes are only part of the story, and often not the most important part when it comes to survival. The final truth this chapter leaves behind is simple and uncomfortable. You can hide from eyes by staying still, blending in, or choosing conditions where visibility fails. But none of those strategies silence the electrical hum of life itself. For a great white shark closing the distance, that hum is enough, and by the time it matters most, it is already listening. The seafloor looks calm only from a distance, a flat expanse of sand rippled by currents and softened by drifting light. But down at the level where bodies meet sediment, it is a crowded and contested space shaped by concealment, pressure, and constant surveillance. This is where stingrays live their double life, not as simple bottom dwellers waiting to be stepped on, but as animals that exist simultaneously as hunted and hunters, reading the substrate beneath them with a sensory system tuned not to sight or sound, but to the faint electrical whispers leaking from living tissue. To understand a stingray properly, the perspective must flip, because this is not an animal defined by aggression alone or vulnerability alone, but by its ability to survive by knowing what lies beneath the surface before it ever makes contact. A stingray's body is built to merge with the sea floor in a way that feels less like camouflage and more like occupation, as if the animal were designed to become part of the sand rather than merely rest upon it. The broad, flattened disc presses low against the substrate, distributing weight so evenly that settling into the sand requires almost no effort, and with a few subtle waves of its pectoral fins, the ray draws sediment over itself until only its eyes and spiracles remain exposed. From above, the outline disappears, broken up by natural coloration that mirrors the mottled patterns of sand and shell fragments. But from below, the picture is even more striking. The ray is not just hiding on the surface, it is positioned directly against the interface where buried life moves, breathes, and betrays itself. This is where the stingray's sensory world diverges sharply from our own assumptions. Vision plays a role, but it is not the primary tool for understanding what lies beneath opaque sand, because light does not penetrate sediment in a way that allows for visual confirmation. Instead, stingrays rely heavily on electroreception, a sense distributed across the head and underside of the body through specialized receptors capable of detecting tiny electrical fields generated by muscle contractions and nerve impulses. These receptors allow the ray to perceive buried animals not as shapes, but as disturbances in an otherwise uniform electrical landscape, transforming the seafloor into something closer to a dynamic map than a static surface. As small fish, worms, crustaceans, and mollusks move beneath the sand, they generate faint electrical signals that leak upward into the surrounding water, signals too weak to matter in open space, but unmistakable at close range when amplified by a body designed to listen for them. The stingray hovers just above the substrate or remains partially buried, its sensory field sweeping the sand like a living metal detector, not in a frantic search, but in a patient scan that rewards stillness. Each twitch beneath the surface adds a point of information, allowing the ray to distinguish between inert debris and living prey without disturbing the sediment at all. In an environment where unnecessary movement can alert predators or waste energy, this ability to sense without touching becomes a powerful advantage. When the ray commits to a strike, the action is sudden but economical, driven by a clear understanding of exactly where the prey is located. Rather than digging blindly or plowing through sand in search of food, which would require significant effort and expose the ray to danger, it uses a rapid downward press of the disc combined with jets of water expelled from the mouth or spiracles to uncover and pin prey in a single motion. This technique is not brute force, it is targeted excavation informed by precise sensory input, ensuring that energy expenditure is minimized and success rates remain high. In shallow environments where food may be patchy and competition intense, efficiency is survival. The same sensory system that makes the stingray an effective hunter also defines its role as a potential victim, because electroreception cuts both ways. A buried ray is not blind to what approaches above the sand, even when visual cues are limited by glare or turbidity. Large predators moving overhead generate their own electrical signatures, distorted by muscle activity and changes in posture, and these signals register long before physical contact becomes a threat. This early warning system allows the ray to react without fully exposing itself, slipping away in a sudden burst of movement that leaves only a cloud of disturbed sand behind, confusing predators that rely on vision alone to track prey. This dual use of electroreception highlights the stingray's position in the ecosystem as both consumer and consumed, navigating a narrow margin where awareness determines outcome. Unlike fast-swimming pelagic animals that can rely on speed to escape danger, rays are built for close contact with the environment, trading outright velocity for control, sensory precision, and the ability to disappear. Their flattened shape, often misunderstood as an evolutionary compromise, is in fact a refinement for life at the boundary between water and sediment, where detecting what cannot be seen is more valuable than outrunning what can. The efficiency of sensing over digging becomes even clearer when considering the energetic costs of life on the seafloor. Digging through sand disrupts not only the substrate, but also the ray's own concealment, increasing exposure to predators and expending calories that must be replaced through feeding. By contrast, sensing allows the ray to remain largely motionless until a strike is guaranteed to succeed, conserving energy and maintaining camouflage. Over evolutionary time, this strategy favors individuals that can interpret subtle signals accurately, shaping a lineage that survives not by constant action, but by informed restraint. There is a quiet tension in this system, because the same sand that provides cover also becomes a medium of vulnerability. For smaller animals that burrow to escape predators, the substrate feels like a barrier, a place to hide from sight and jaws. Yet for a stingray scanning from above, it is little more than a filter through which life announces itself. The movements of buried prey leave traces that cannot be fully suppressed, turning the sand into a screen on which activity is displayed in electrical patterns rather than images. In this sense, the stingray does not hunt the sand, it reads it, interpreting signals that reveal where life persists beneath the surface. This dynamic reshapes how the seafloor functions as a habitat. Burrowing organisms are not simply hidden. They are part of an ongoing exchange of information that predators like stingrays exploit. This pressure influences how prey move, how long they remain active, and how deeply they burrow, driving adaptations that ripple through the community. The presence of stingrays alters behavior even when they are unseen, because the threat they represent is not tied to visibility, but to proximity and activity, reinforcing the idea that safety is relative and temporary in this environment. The irony of the stingray's reputation lies in how often it is framed as a passive hazard rather than an active participant in the ecosystem. Encounters with humans tend to focus on accidental injuries, moments when a hidden ray defends itself against perceived threats, overshadowing the reality that this animal spends most of its life engaged in a complex balancing act of sensing, feeding, and avoiding detection. The defensive spine, while effective, is a last resort rather than a defining feature, used when concealment fails and escape is not immediate. The real story is not about the sting, but about the unseen sensory dialogue playing out across the seafloor every moment of the day. Understanding stingrays in this context reframes the sand itself as an active zone rather than empty space, a layer thick with information that some animals can read and others cannot. What appears safe to the untrained eye is, in reality, constantly monitored by organisms tuned to signals beyond vision. The ray's body becomes an interface between worlds, bridging the gap between buried life and open water, translating electrical cues into decisive action. This perspective challenges the assumption that danger announces itself through movement or visibility, revealing instead a system where threat is often silent and proximity matters more than awareness. The final truth carried by this chapter is unsettling in its simplicity. The sand is not a refuge, and stillness is not invisibility. Beneath the calm surface lies a network of signals that betray life to those equipped to sense it. And somewhere just above or within the sediment, a stingray may already be reading the ground beneath you, deciding when to move. At first glance, a manta ray seems like the ocean's most harmless indulgence, a creature shaped more by elegance than intent, drifting through open water with a wingspan that feels oversized for any animal that appears so calm. It moves without urgency, its pectoral fins rising and falling in slow, deliberate strokes that resemble flight more than swimming. And for many observers, this visual language suggests passivity, even naivety, as though the manta were simply carried by the sea rather than actively engaging with it. This perception is reinforced by its diet, its lack of teeth designed for tearing flesh, and its reputation as a gentle giant that tolerates the presence of other animals, including humans, without aggression. Yet this surface narrative collapses when you stop watching the manta as a spectacle and begin observing it as a navigator, a sensor platform, and a highly specialized organism evolved to read an ocean that is anything but random. The open ocean is not empty space, even though it often appears that way to the human eye, because its structure is defined less by visible landmarks and more by movement, gradients, and invisible boundaries created by currents, temperature differences, and biological activity. Plankton, the foundation of marine food webs, does not disperse evenly. It accumulates in dense patches where water masses converge, where upwellings bring nutrients to the surface, or where tidal flows compress drifting organisms into narrow corridors of abundance. These zones shift constantly, forming what could be described as invisible highways of food that exist for hours or days before dissolving and reforming elsewhere. To survive on plankton at the scale of a manta ray requires more than simply swimming with an open mouth. It demands the ability to locate, follow, and remain within these moving concentrations without wasting energy on empty water. This is where the manta ray's sensory world diverges sharply from the simplistic image of a drifting filter feeder. Like sharks and many other cartilaginous fishes, mantas possess ampullae of Lorenzini, specialized electroreceptive organs distributed primarily around the head that are capable of detecting weak electric fields in the surrounding water. These structures are often associated exclusively with predatory behavior, particularly in animals that hunt buried or camouflaged prey. But in mantas, their function expands into a broader role that includes spatial awareness, navigation, and fine-scale assessment of biological activity. Every living organism generates an electrical signal through muscle contractions and nerve impulses, and in areas where plankton density increases, the cumulative effect of countless microscopic movements subtly alters the electrical landscape of the water. To a manta ray, these changes are not abstract. They are tangible cues that indicate where life is concentrated. As a manta glides through a current rich with plankton, it is not merely reacting to what it sees at the last moment, nor is it feeding blindly and hoping for success. Instead, it is sampling the water continuously, integrating information from electroreception, mechanoreception through its lateral line, and subtle pressure changes across its broad body surface. The manta's large size, often perceived as a liability in a world dominated by agility, becomes an advantage here, because it allows the animal to detect gradients over a wider area, effectively turning its body into a sensor array that feels the shape of the flow itself. Slight increases in resistance, shifts in current direction, and changes in electrical noise all contribute to a dynamic map that guides the manta along routes of maximum reward. This ability to read the ocean transforms feeding from a random search into a directed journey. When mantas are observed returning repeatedly to specific locations at particular times, such as coastal cleaning stations or seasonal aggregation sites, it is tempting to attribute this behavior solely to memory or learned routes, and while those factors play a role, they do not fully explain how mantas locate transient plankton blooms that leave no permanent trace. Electroreception provides a mechanism for detecting biological activity even before it becomes visually obvious, allowing mantas to adjust their path in response to signals that precede visible density. In this way, the manta does not chase food in the traditional sense. It aligns itself with moving systems, positioning its body within flows that deliver nourishment continuously as long as the conditions persist. The cinematic effect of this strategy becomes apparent when a manta enters a feeding spiral or joins a chain of other mantas circling within a plankton-rich current. From the outside, the behavior looks almost ritualistic, as if the animals were following an unseen choreography. But beneath the surface, each individual is responding to the same sensory information, fine-tuning its position to remain within the narrow band where intake is maximized and effort minimized. The cephalic fins unfurl to guide water into the mouth, But the real work is done before feeding even begins, through the selection of the path itself. A manta that misreads the flow or fails to detect the subtle cues indicating concentration will expend enormous energy for little return, while one that reads the signals correctly can feed efficiently for hours. This sensitivity to invisible structure also plays a role in long-distance movement, challenging the notion that mantas wander aimlessly across vast expanses of ocean. Migration in mantas is not fully understood, but evidence suggests that their movements are closely tied to productivity cycles, current systems, and the shifting availability of plankton. Electroreception may contribute to this process by allowing mantas to sense large-scale biological gradients over time, reinforcing pathways that consistently lead to feeding opportunities. In this context, the ocean is not a featureless plain, but a layered environment with corridors, bottlenecks, and junctions defined by physics and life interacting at scale. The irony of the manta's gentle image lies in how easily it obscures the sophistication required to survive on such an ephemeral resource. Feeding on plankton demands constant intake and precise positioning, because individual prey items are tiny and energy-rich only in aggregate. A predator that relies on speed or ambush can afford periods of inactivity between meals, but a filter feeder of this size cannot. The manta's calm demeanor is not a sign of simplicity, but of confidence in a system it understands deeply, moving with purpose through an environment it reads continuously rather than reacting to impulsively. This perspective reframes the manta ray not as a passive drifter, but as an active participant in the ocean's circulation, a living indicator of where energy flows converge and disperse. Its presence marks zones of productivity, and its movements reflect changes in the underlying structure of the sea that remain invisible to surface observation. In this way, mantas become ambassadors of a hidden order, revealing that the ocean's apparent emptiness conceals a network of roots and rhythms that govern the distribution of life. The final realization this chapter leaves behind is both elegant and unsettling in its simplicity. The ocean is not chaos, and food does not appear by chance. There are lanes, intersections, and currents of opportunity moving beneath the surface, and while humans see only water, mantas feel the traffic itself. The first thing that collapses when you try to understand a blue whale is scale, because the ocean does not operate on the distances your eyes are trained to measure, and neither does the largest animal ever to live within it. Light fades quickly underwater, absorbed and scattered until even the clearest seas reduce vision to a narrow bubble around the body, a limitation that makes sight unreliable for navigation, coordination, or long-range awareness. Sound, however, behaves differently, traveling faster and farther in water than in air, bending with temperature layers and pressure gradients, slipping through darkness and turbidity with ease. In this environment, distance is not something you see, it is something you hear. And the blue whale is built to exist at the extreme end of that acoustic reality. A blue whale moves through a three-dimensional world that is constantly shifting, where prey appears and disappears in vast ephemeral blooms driven by currents, temperature fronts, and seasonal cycles. Krill, the tiny crustaceans that sustain these giants, do not form permanent landscapes, but transient clouds that can stretch for kilometers one week and vanish the next, pulled apart by changing conditions. To survive on such a resource at such an immense scale requires more than a large mouth and efficient feeding mechanics. It requires a way to stay connected to a world too large and too dynamic to be tracked visually. The blue whale solves this problem not with speed or aggression, but with sound, producing some of the lowest frequency vocalizations known in the animal kingdom, signals that roll through the ocean like seismic waves rather than sharp calls. These low-frequency sounds, often below the threshold of human hearing, can travel enormous distances under the right conditions, sometimes spanning entire ocean basins when guided by deep sound channels created by layers of temperature and pressure. Unlike high-frequency noises that dissipate quickly, low-frequency vibrations lose little energy as they propagate, allowing a single call to persist long after the whale that produced it has moved on. For the blue whale, this is not simply a means of announcing presence or attracting mates. It is a way of anchoring itself within a space that is otherwise too vast to comprehend, maintaining acoustic contact with others across distances that would render visual cues meaningless. The idea that communication is central to survival becomes clearer when you consider the scale mismatch between the whale and its food. A blue whale can weigh more than many ships, yet it feeds on organisms small enough to fit on the tip of a finger, creating an ecological paradox where the largest body depends on some of the smallest prey. Coordinating movements toward productive feeding grounds becomes critical, because wandering blindly through empty water would be catastrophically inefficient. Low-frequency calls provide a mechanism for sharing information about location, movement, and perhaps even environmental conditions, allowing whales to align their migrations with shifting zones of abundance. In this context, sound becomes a form of collective navigation, a way to map a moving world without ever seeing it in its entirety. Hearing, rather than sight, becomes the primary sense through which blue whales experience their environment, not only because sound travels farther, but because it carries information about structure, distance, and change in a medium where visual reference points are scarce. The ocean is layered, with thermoclines and currents creating invisible boundaries that shape where life can thrive, and sound interacts with these layers in predictable ways. By producing and listening to low-frequency calls, blue whales may gain insight into the acoustic character of their surroundings, detecting reflections, distortions, and shifts that signal changes in depth, temperature, or the presence of large features such as continental shelves. This sensory relationship turns vibration into geography, allowing the whale to navigate a planet-sized space through resonance rather than landmarks. The physical act of producing these sounds reflects the blue whale's extreme adaptations to life at scale. Air is moved through massive respiratory structures, and vibrations are generated within tissues designed to handle immense pressure changes during deep dives. These calls are not casual expressions but energetically significant events, carefully modulated and timed to maximize range and effectiveness. A single vocalization represents a deliberate investment of energy, justified only because of its potential to reach distant receivers and influence movement across vast areas. In a world where visibility may extend only a few body lengths, such investments make sense, transforming sound into the most reliable currency of information. There is a humbling irony in the fact that an animal so large relies on something as intangible as vibration to make sense of its world. The blue whale does not dominate the ocean through force or speed, but through its ability to integrate into its acoustic fabric, becoming both a source and a receiver of the low-frequency background that defines its habitat. This acoustic presence is not constant noise, but structured communication shaped by behavior, season, and context, rising and falling as whales migrate, feed, and interact. To exist as a blue whale is to live inside a soundscape that stretches far beyond the horizon, where individual calls overlap and echo, creating a shared auditory environment that binds distant individuals into a loose but persistent network. The limitations of vision in water further emphasize the importance of this auditory world. Light is absorbed unevenly, colors vanish with depth, and even large objects can disappear into blue haze at surprisingly short distances. For an animal that may spend hours submerged and travel thousands of kilometers over a year, relying on sight alone would be inadequate. Hearing fills that gap, offering continuity in a medium that otherwise fragments perception. Through sound, blue whales can maintain awareness of others, detect changes in the environment, and orient themselves within migratory corridors that are invisible but acoustically consistent. This reliance on sound also reveals how vulnerable these animals are to changes in the acoustic environment. Human-generated noise from shipping, sonar, and industrial activity adds layers of interference to a system evolved for subtle, long-range communication. Low-frequency noise overlaps directly with the frequencies used by blue whales, potentially masking signals that once traveled freely across ocean basins. In a sensory world dominated by sound, such interference is not a minor inconvenience, but a fundamental disruption of the whale's ability to navigate, coordinate, and survive. Understanding blue whales therefore requires recognizing that their habitat is not just water, but vibration, and that altering that vibration alters the space they inhabit. Despite these challenges, The blue whale's existence remains a testament to the power of adaptation at scale. Its massive body, often perceived as cumbersome, is perfectly suited to long-distance travel, storing energy efficiently and moving with surprising grace through open water. Its feeding strategy, synchronized with seasonal productivity, aligns with migrations guided not by sight, but by acoustic memory and collective signaling. Its social structure, often subtle and dispersed, is maintained through sound that transcends physical separation, allowing individuals to remain connected even when oceans apart. When you step back and consider this system as a whole, the idea of scale shifts again, no longer centered on size alone, but on reach. The blue whale's influence extends far beyond its immediate presence, carried outward through low-frequency calls that ripple across the sea, interacting with layers of water shaped by planetary forces. In this sense, the whale is not merely moving through the ocean. It is embedded within its dynamics, participating in cycles that span seasons and continents. Its voice becomes part of the ocean's background, a reminder that life at this scale does not operate in isolation, but in resonance with the environment itself. The final feeling left by this perspective is one of profound smallness, not in relation to the whale's body, but in relation to the sensory world it inhabits. While humans navigate primarily by sight and immediate surroundings, blue whales navigate a planet-sized space through sound, mapping distance with vibration and coordinating existence across vast, unseen corridors. The ocean is not silent, and it never has been. It carries a soundtrack shaped by physics, biology, and movement. And the blue whale lives entirely within it, listening, calling, and traveling through a world defined not by what can be seen, but by what can be heard. At the boundary where rivers lose their certainty and the ocean begins to intrude, where fresh water turns brackish and visibility collapses into suspended silt, crocodiles become the dominant interpreters of chaos. These environments are hostile to sight, not only because the water is muddy, but because light itself fractures under shifting surfaces, mangrove shadows and drifting debris, turning vision into an unreliable sense that can betray more than it informs. In these estuaries and coastal swamps, the crocodile thrives not by seeing clearly, but by abandoning the expectation that sight should matter at all. It exists in a sensory world built around pressure, vibration, and timing, a world where movement itself becomes information and where the smallest disturbance can reveal intent long before the body responsible for it is visible. A crocodile's body appears primitive at a glance, heavy and armored, pressed low against the waterline with eyes and nostrils positioned just above the surface, as if the animal were designed solely to watch. In reality, this posture is not about looking, but about listening through the skin. Along the crocodile's jaws and body are thousands of tiny sensory organs, known as integumentary sensory organs, each capable of detecting minute changes in water pressure caused by movement nearby. These receptors turn the surface of the water into a sensitive membrane, allowing the crocodile to perceive ripples, splashes, and waves as spatial data rather than noise. In muddy water, where a fleeing animal might remain invisible until the final second, pressure waves travel cleanly, announcing direction, distance, and speed with ruthless honesty. The effectiveness of this system becomes apparent when observing how little a crocodile needs in order to react. A single misplaced step at the water's edge, a foot entering the river with a slight kick, or the faint oscillation caused by an animal swimming across a channel is enough to trigger a response. The crocodile does not turn its head in panic or surge forward impulsively. Instead, it makes a subtle adjustment, a barely perceptible change in angle that aligns its body with the source of the disturbance. This adjustment happens before the prey registers danger, because the crocodile's sensory input precedes visual awareness. By the time the surface reflects a shape or a shadow, the crocodile has already calculated the geometry of the encounter. This calculation is the heart of the crocodile's hunting strategy, and it explains why these animals rarely chase prey over long distances. Chasing in shallow, cluttered water is inefficient and risky, exposing the crocodile to injury and wasting energy that is difficult to replace in environments where meals are unpredictable. Instead, Crocodiles wait until the prey has committed to a movement that cannot be undone. A swimmer crossing a channel, an animal stepping down a muddy bank, or prey entering deep water has already limited its options. And the crocodile's role is not to pursue, but to intercept. The sensory system informs not only where the prey is, but when escape routes are closing, turning patience into a weapon as effective as any set of teeth. The surface of the water becomes a kind of ledger, recording every action taken by living bodies that break its tension. Each ripple spreads outward, intersecting with others, creating patterns that a crocodile reads instinctively. A fast, panicked splash carries different information than the slow, rhythmic disturbance of an animal wading cautiously, and the crocodile's response varies accordingly. This discrimination is critical, because reacting too early can alert prey and spoil the opportunity, while reacting too late can allow the moment to pass. The crocodile's stillness is not inactivity, but a state of continuous assessment, an internal process that weighs movement against distance, speed against angle, and commitment against escape. The physical placement of the crocodile's eyes and nostrils reinforces this strategy, allowing it to remain almost entirely submerged while monitoring the surface for disturbances. From this position, the animal presents minimal profile, reducing the chance of detection while maximizing sensory input. The jaws, lined with pressure-sensitive receptors, sit just beneath the surface, ready to close with explosive force once the decision is made. The result is an ambush predator that does not need to see its prey clearly, because clarity is unnecessary when the outcome has already been decided by physics. This reliance on vibration and pressure extends beyond hunting and into the crocodile's broader relationship with its environment. Crocodiles are acutely aware of changes in water level, current speed, and seasonal flow patterns, all of which influence prey movement and availability. During floods, when water spreads into new areas, crocodiles reposition themselves to intercept animals displaced by rising levels, using the same sensory cues to locate crossings and bottlenecks. During dry seasons, they concentrate around shrinking pools and channels, where prey is forced to approach the water to drink. In each case, the crocodile's success depends less on aggression than on understanding how animals move when their options are constrained. The unsettling aspect of this system lies in how little warning it provides to those unfamiliar with it. Humans, accustomed to relying on vision as a primary indicator of danger, often mistake the absence of visible threat for safety, stepping into water or approaching banks without realizing that their movement has already been registered. The crocodile does not need to announce itself or rush forward dramatically. The decision to strike is made quietly, based on sensory input that humans do not perceive. By the time the animal reacts visibly, the encounter has already reached its irreversible phase. From an evolutionary perspective, this sensory specialization represents an elegant adaptation to environments where traditional senses fail. Muddy rivers, mangrove swamps, and estuaries are not marginal habitats, but highly productive ones, rich in life precisely because they are difficult to navigate. Crocodiles exploit this difficulty, turning low visibility into an advantage by shifting the sensory balance away from sight and toward mechanical detection. This allows them to dominate spaces where faster, visually oriented predators struggle, reinforcing their role as apex predators in these ecosystems. The crocodile's reputation as a relic of the past often obscures the sophistication of this system. While their lineage stretches back millions of years, their success is not due to stagnation, but to refinement, with sensory adaptations honed by countless encounters in complex environments. The integration of vibration detection, pressure sensing, and calculated timing creates a predator that is remarkably consistent in its effectiveness, capable of surviving dramatic environmental changes that have eliminated less adaptable species. Understanding crocodiles through this lens also reframes their interactions with prey species, which have evolved their own strategies to minimize risk. Animals that share these habitats learn to approach water cautiously, testing the surface with minimal disturbance, or choosing entry points where visibility and escape routes are more favorable. These behaviors reflect an ongoing arms race, shaped not by speed or strength, but by information, where survival depends on who can read the environment more accurately and act with greater restraint. The final lesson delivered by the crocodile's hunting strategy is both simple and deeply uncomfortable. In these waters, Danger does not announce itself through sight or sound, and absence of evidence is not evidence of absence. The crocodile does not need to be seen to act, because it is not waiting for visual confirmation. It is waiting for you to move, because movement is truth in a world where sight lies. In clear, sunlit water, where visibility stretches far enough to create the illusion of safety, the barracuda becomes the embodiment of a different kind of threat, one that depends not on concealment or patience alone, but on speed so sudden that awareness itself becomes irrelevant. These are not hunters of murk or darkness, nor interpreters of vibration or sound in the way crocodiles or sharks dominate their domains. Barracudas rule the bright zones of reefs, lagoons, and drop-offs, where light sharpens edges and motion becomes unmistakable. In this environment, survival favors those who can see first and react faster than thought. And the barracuda is built precisely for that equation, turning vision into a weapon and acceleration into a verdict delivered before panic has time to form. At rest, a barracuda looks deceptively idle, hovering in the water column with a posture that suggests indifference rather than intent. Its elongated body remains rigid, held almost perfectly straight, while subtle adjustments of the fins keep it suspended with minimal effort. The head is blunt and oversized relative to the rest of the body, the jaws lined with prominent teeth that seem excessive for an animal that often appears motionless. This stillness is not passive waiting, but a calculated stance that maximizes sensory input while minimizing energy expenditure. In bright water, where even small movements can ripple through a school and trigger collective flight responses, remaining perfectly still allows the barracuda to observe without announcing itself, blending into the visual noise of reef shadows and sun streaks. Vision dominates everything about the barracuda's hunting strategy, and its eyes reflect that priority. Positioned forward enough to provide strong binocular overlap, the eyes allow precise depth perception, critical for judging distance and timing during high-speed strikes. The retina is adapted for bright conditions, capable of resolving fine detail and detecting rapid changes in position, which means that the barracuda does not simply notice movement, but analyzes trajectories. It watches how fish within a school adjust their spacing, how individuals hesitate or drift slightly out of alignment, and how micro-patterns of motion betray weakness. In a tightly coordinated school, safety lies in uniformity, but perfect uniformity is rare, and the barracuda's gaze is tuned to detect the slightest deviation that marks an opportunity. Unlike predators that pursue and adapt mid-chase, the barracuda operates on interception rather than tracking. Tracking requires constant adjustment, processing feedback over time, and reacting to unpredictable maneuvers, all of which introduce delay. Interception, by contrast, is decisive and brief, relying on an accurate prediction of where prey will be, rather than where it is now. The barracuda watches the movement of the school, calculates angles subconsciously through evolved neural circuitry, and selects a path that cuts through space ahead of the target rather than behind it. Once the strike begins, there is no reassessment, no correction, only commitment, because hesitation at these speeds would mean failure. The physical structure of the barracuda supports this strategy with ruthless efficiency. Its body is shaped like a missile, long and narrow with minimal drag, built to accelerate explosively in a straight line rather than sustain prolonged pursuit. Powerful muscles along the flanks store energy during stillness, releasing it in a sudden burst that propels the animal forward faster than most reef fish can react. The tail delivers the final thrust, snapping with enough force to close distances in fractions of a second, while the rest of the body remains rigid, channeling momentum directly toward the target. This design prioritizes initial acceleration over endurance, reflecting a lifestyle where success or failure is determined almost instantly. The strike itself is brief and brutal, not because of violence for its own sake, but because speed leaves no room for prolonged struggle. The barracuda launches from stillness, its body blurring as it covers several body lengths in the time it takes prey to register a threat. The jaws open just enough to seize, not to clamp down indiscriminately, and the teeth, sharp and uneven, are positioned to grip and slice in a single motion. There is no chase, no swirling pursuit through the school, only a flash of silver and a sudden gap where a fish once was. For the remaining members of the school, panic erupts only after the strike is complete, their synchronized movement dissolving into chaos too late to save the targeted individual. This reliance on visual clarity explains why barracudas are most effective in bright water, where light enhances contrast and movement becomes easier to read. In these conditions, fear spreads quickly through schools because visibility allows prey to see each other's reactions, amplifying panic and creating opportunities for secondary strikes. Barracudas exploit this by positioning themselves near edges of schools or along natural corridors, such as reef walls or drop-offs, where escape routes narrow and confusion increases. They do not need to pursue every fleeing fish. They only need one moment of disorganization to reset the conditions for another interception. There is a cruel elegance to this system because it turns the prey's own survival strategy into a vulnerability. Schooling evolved to confuse predators through coordinated movement, but that coordination depends on constant visual alignment. When a school reacts to a sudden strike, individuals momentarily break formation, creating precisely the kind of visual irregularities that the barracuda excels at detecting. In this way, panic itself becomes a signal, advertising weakness in the same visual language the barracuda already understands. The predator does not need to induce chaos deliberately. It simply benefits from the inevitable breakdown that follows an attack executed at extreme speed. Energy efficiency underpins this behavior, even if it appears extravagant. Explosive acceleration is costly, but the brevity of the strike minimizes total expenditure, and the high success rate justifies the investment. Barracudas do not waste energy on prolonged chases that may end in failure. They strike when conditions are optimal and disengage when they are not. This pattern reflects a broader ecological role as opportunistic predators that shape the behavior of prey species without constantly consuming large numbers of individuals. The threat of interception influences how fish schools position themselves, how they move through open water, and how they respond to sudden disturbances, reinforcing the barracuda's presence even when it is not actively feeding. The sensory emphasis on vision also explains the barracuda's notorious reactions to reflective objects which mimic the flashes of scales that signal prey in distress. In bright water, sudden glints stand out sharply against the background, triggering instinctive responses that have been reinforced over evolutionary time. This sensitivity is not stupidity or aggression, but a byproduct of a visual system tuned to prioritize certain cues over deliberation. When survival depends on acting before thought, false positives are less costly than missed opportunities, especially in environments where prey is abundant and encounters are frequent. Despite their fearsome reputation, barracudas are not reckless killers roaming endlessly in search of conflict. They are selective, timing-dependent predators that wait for the precise alignment of light, movement, and vulnerability before committing to action. Their apparent boldness masks a reliance on conditions that favor success. And when those conditions are absent, they conserve energy through stillness rather than futile pursuit. This balance between explosive action and prolonged restraint defines their ecological niche, allowing them to coexist with other predators that rely on different sensory strategies. Understanding barracudas through this lens also reveals how specialized their dominance truly is. In low visibility or complex habitats where vision is compromised, they lose their advantage, yielding ground to predators that read vibration, scent, or electrical cues more effectively. Their power lies not in versatility, but in mastery of a specific sensory domain, one where light and motion converge to create moments of absolute clarity. In that domain, reaction speed becomes destiny, and hesitation is fatal. The unsettling truth at the core of the barracuda's strategy is that the kill begins long before the prey recognizes itself as a target. The decision is made during stillness, in the silent calculations of angles and speed, while the prey continues to swim unaware, convinced by bright water and open space that danger would be visible if it existed. By the time panic erupts, the outcome is already sealed, because the fastest kill is not the one that ends quickly, but the one that starts before fear has time to form. The deep sea does not reward speed, vision, or strength in the ways that shallow water does, because at depth, the rules of perception collapse under pressure, darkness, and scarcity, leaving deception as one of the most effective survival strategies available. This is the realm of the monkfish, also known as anglerfish, an animal that does not hunt by chasing or ambushing in the traditional sense, but by falsifying reality itself. In a world where light is rare and food rarer still, the monkfish survives by turning the most basic survival instinct of other animals against them, offering not pursuit or violence, but a lie so convincing that prey swims willingly into its own erasure. Down here, darkness is not simply the absence of light, but a defining physical condition that shapes every interaction. Sunlight does not reach these depths, and bioluminescence becomes the dominant visual language, used sparingly and purposefully by organisms that cannot afford to waste energy. Every flash, glow, or pulse carries meaning, signaling presence, danger, or opportunity, and in this environment, seeing something at all is often interpreted as a reason to approach rather than retreat. The monkfish exploits this assumption with ruthless efficiency, anchoring itself to the seafloor or hovering just above it, its grotesquely proportioned body blending into the surrounding rock and sediment, while a single glowing point dances in front of its face like an invitation. That glowing point is not incidental decoration, but a highly specialized structure, a modified dorsal spine known as an elytium, tipped with a fleshy bulb called the esker that functions as bait. This is not metaphorical language. The structure is evolution's answer to fishing equipment, a rod and lure built directly into the predator's body. The monkfish can wiggle, pulse, or hold the esker perfectly still, mimicking the movement patterns of small prey or drifting organic matter, calibrated to match the expectations of animals navigating near total darkness. To a passing fish or crustacean, the glow suggests food, safety, or curiosity rather than danger, because in the deep sea, opportunities are so rare that hesitation can be fatal. What makes this system profoundly unsettling is that in many monkfish species, the light itself is not produced by the fish's own cells, but by symbiotic bioluminescent bacteria housed within the esker. These bacteria generate light through chemical reactions, fed and maintained by the host, creating a living lantern whose glow is outsourced to another organism entirely. This arrangement represents an extreme form of biological cooperation, where the monkfish provides shelter and nutrients, and the bacteria provide a tool of deception that benefits both parties. The fish gains an irresistibly realistic lure, while the bacteria gain a stable environment in which to thrive, their light serving a purpose far removed from communication or warning. This outsourced glow technology allows the monkfish to fine-tune its deception in ways that purely self-generated light might not allow. The intensity, color, and persistence of the glow can be modulated through subtle control of the esker, ensuring that the signal remains convincing without drawing unwanted attention from larger predators. In the deep sea, where every energy expenditure matters, this precision reduces risk while maximizing reward. The monkfish does not advertise itself broadly. It broadcasts just enough to draw in prey that is already searching desperately for its next meal. The sensory trap is devastating because it targets the way prey interpret their environment under extreme conditions. In darkness, vision becomes less about identifying shapes and more about responding to contrast and movement, and the brain of a small fish is wired to associate faint points of light with bioluminescent organisms that are often edible or harmless. The monkfish leverages this bias perfectly, positioning its lure just beyond the reach of its own body, creating a false sense of separation between the glowing point and the mass of the predator itself. Prey approach cautiously but optimistically, closing the distance without ever registering the outline of the fish waiting beneath. The strike, when it comes, is not dramatic in duration but overwhelming in scale. The monkfish's mouth opens with astonishing speed, expanding to a size that seems incompatible with the rest of its body, creating a sudden pressure change that pulls water and prey inward. Teeth angled inward prevent escape, and the jaws close before the prey can process the transition from opportunity to annihilation. There is no chase, no struggle, and no correction, because the decision was made by the prey the moment it interpreted the glow as food rather than threat. In this sense, the monkfish does not kill by force alone, but by manipulating perception so completely that resistance never occurs. This strategy makes perfect ecological sense in an environment defined by energy scarcity. Deep-sea organisms cannot rely on frequent meals, and failed hunts carry a higher cost than in productive surface waters. The monkfish avoids wasted effort by allowing prey to come to it, conserving energy through prolonged stillness, broken only by brief, decisive action. Its body reflects this economy, with reduced musculature for sustained swimming and a reliance on buoyancy and camouflage to maintain position. The grotesque proportions that often shock human observers are not inefficiencies, but adaptations tuned for a lifestyle where deception outweighs agility. The horror of this system lies not in gore or violence, but in the quiet inevitability of the outcome. Prey are not chased down or overwhelmed through superior speed, they are convinced. The glow does not threaten, rush, or intimidate. It invites, exploiting curiosity and hunger in equal measure. In a world where seeing anything at all can feel like hope, the monkfish turns hope into a liability, proving that information itself can be weaponized. This method of hunting also reshapes the behavior of deep-sea prey species, which evolve heightened sensitivity to context and subtle cues, learning to distinguish between genuine bioluminescent signals and potential traps. Yet the balance is delicate, because avoiding every glow could mean missing rare feeding opportunities, while approaching the wrong one means death. The monkfish thrives in this uncertainty, occupying the narrow space between caution and desperation that defines survival at depth. There is a bitter irony in the fact that the deep sea, often imagined as empty and lifeless, supports such intricate psychological warfare between organisms that may never encounter one another more than once. The monkfish embodies this contradiction, existing as a stationary node of deception in a vast, sparsely populated environment, relying on the predictable vulnerabilities of animals shaped by scarcity. Its success is not measured by dominance over territory or frequent kills, but by patience and timing, by waiting for the moment when another creature's need overrides its caution. Understanding the monkfish forces a re-evaluation of what hunting means when visibility, speed, and strength are stripped away. In the deep sea, the most effective predators are not those that can overpower, but those that can manipulate signals, turning the sensory rules of the environment into traps. Light, usually associated with safety and clarity, becomes a tool of fraud, and perception itself becomes the battlefield. The final realization this chapter leaves behind is unsettling precisely because it feels so modern. In the deep ocean, survival often depends on interpreting signals correctly, and the monkfish survives by broadcasting false ones. There is no honor, no pursuit, and no warning, only a fabricated invitation and a consequence that arrives too fast to reconsider. In that sense, deep-sea hunting is not about teeth or strength at all, but about deception refined to its purest form, a reminder that in the darkest places on Earth, the most dangerous predators are not the ones you see, but the ones that convince you to come closer. Water changes the meaning of distance, and nowhere is that more apparent than in the world of sea snakes, where the boundary between air and ocean dissolves into something navigable, breathable, and readable in ways that feel alien to terrestrial instincts. These reptiles do not merely tolerate the sea, they move through it with the confidence of animals that have rewritten the rules of what a snake can be, flattening tails into paddles, sealing lungs for extended dives, and evolving sensory systems that treat currents not as obstacles, but as information. In reef systems where visibility fractures into shifting glare and shadow, where rocks, coral heads, and sediment create endless hiding places, the sea snake survives not by seeing better, but by knowing how to follow what cannot be seen. The reef itself is a maze, dense with crevices, overhangs, and tunnels that provide refuge for small fish and eels fleeing larger visual predators. From a human perspective, this complexity feels protective, a place where prey can vanish by slipping into a crack too small for pursuit. For a sea snake, however, these hiding places are not barriers but funnels, because every living animal moving through water leaves behind a chemical signature that disperses slowly, clinging to surfaces and drifting along currents like a lingering echo. The ocean does not erase scent the way air does. It stretches it, smears it, and preserves it just long enough to be read by predators, evolved to interpret chemical landscapes rather than visual ones. The key to this ability lies in the sea snake's tongue, which flicks rhythmically in and out, sampling the water with each movement. This behavior is often misunderstood as tasting, but it is closer to smelling with the mouth, a process in which microscopic chemical particles are collected on the tongue's surface and transferred to the vomeronasal organ, a specialized sensory structure that decodes chemical information with remarkable sensitivity. On land, snakes use this system to track prey across soil and vegetation, following trails that persist on surfaces long after an animal has passed. In water, the same principle applies, but the medium transforms the trail into a three-dimensional plume shaped by currents, eddies, and the contours of the reef itself. As a sea snake moves through this environment, it is not swimming aimlessly or scanning for shapes in the distance. It is reading gradients, detecting changes in chemical concentration that indicate direction and recency, adjusting its path with subtle movements that align it more closely with the source. Each tongue flick provides a data point, and over time, these points form a map that leads unerringly toward prey, even when that prey remains completely hidden from view. This is why sea snakes can hunt effectively in turbid water, at dusk, or within tangled reef structures where eyesight offers little advantage. The prey species targeted by sea snakes reflect this sensory specialization. Many feed on small reef fish, eels, or burrowing organisms that rely on concealment rather than speed, retreating into cracks or holes at the first sign of danger. Against a visually oriented predator, this strategy often works because once the prey disappears into the reef, the hunter loses its target. Against a sea snake, however, hiding only concentrates the chemical signal, trapping scent within confined spaces where it becomes easier to follow. The snake does not need to see into the crevice. It only needs to confirm that the trail leads there, and once it does, the geometry of escape narrows dramatically. The body of the sea snake supports this methodical approach, slender and flexible enough to probe into tight spaces while maintaining control in moving water. Unlike many terrestrial snakes, sea snakes possess laterally compressed tails that provide efficient propulsion, allowing them to hover, reverse, and pivot with precision as they investigate scent sources. Their lungs extend along much of the body length, aiding buoyancy control and allowing fine adjustments in depth without constant swimming, which in turn reduces disturbance to the water and preserves the integrity of the chemical trail being followed. This quiet movement is not incidental. It is essential for maintaining access to information that would be disrupted by turbulence. The danger inherent in this system lies in its subtlety, because a predator that hunts primarily through chemical cues does not need to announce itself visually. In low visibility conditions, a human swimmer or diver may see nothing at all, assuming safety in the absence of obvious threats, while a sea snake nearby has already detected the chemical traces left by movement, skin contact with water, or the disturbance of sediment. The snake's approach is often calm and unhurried, not because it lacks intent, but because it does not need to rush. The trail leads forward regardless of speed, and patience increases accuracy. Venom adds another layer to this strategy, though it is rarely displayed in dramatic fashion. Sea snake venom is among the most potent of all reptiles, evolved to subdue prey quickly in an environment where prolonged struggle would be costly and risky. A rapid immobilization prevents prey from retreating deeper into the reef or damaging the snake during capture. Yet despite this potency, sea snakes are generally non-aggressive, conserving venom for feeding rather than defense, an economy that reflects the high metabolic cost of venom production. Their threat is real but understated, woven into their hunting efficiency rather than broadcast as intimidation. The evolutionary journey that led snakes into the sea underscores how adaptable this lineage is when given enough time and selective pressure. Sea snakes retain many reptilian traits, such as ectothermy, relying on external heat sources to regulate body temperature, which ties their activity patterns closely to water temperature and sun exposure. They often bask at the surface or in warm shallows to elevate body temperature before hunting, optimizing muscle performance and sensory processing. This thermoregulatory behavior interacts with their chemical sensing, because warmer water can alter scent dispersion, subtly changing how trails are read and followed. In this way, even temperature becomes part of the information landscape. Migration and movement patterns in sea snakes also reflect a sensitivity to chemical and environmental cues rather than visual landmarks. Seasonal shifts in prey availability, water temperature, and current patterns influence where snakes concentrate their activity, often leading to localized aggregations that coincide with spawning events or increased prey density. These movements are not random, but guided by a combination of learned routes and real-time sensory input, demonstrating that chemical perception scales beyond individual hunts to shape broader ecological patterns. The presence of sea snakes influences the behavior of reef communities in ways that are easy to overlook because they operate below the threshold of visibility. Prey species may adjust activity times, reduce movement, or choose different shelter types in areas where chemical cues indicate higher predation risk. This creates a feedback loop in which the snake's hunting method shapes not only individual encounters, but the spatial and temporal structure of reef life. Even when a snake is not actively hunting, its sensory reach extends beyond its physical presence, altering behavior through the persistent possibility of detection. There is an irony in how unfamiliar this mode of hunting feels to humans who prioritize sight and sound and often underestimate the richness of chemical information in aquatic environments. To us, water appears to wash things away, to dilute and obscure, yet to animals like sea snakes, it preserves and distributes clues with remarkable fidelity. The ocean becomes a tapestry of trails layered over one another, some fading, some fresh, all readable to those equipped to interpret them. In such a system, secrecy is fragile, and movement carries consequences long after it occurs. Understanding sea snakes through this lens shifts the narrative away from fear toward respect for a predator that operates with quiet precision. Their presence reminds us that danger in the ocean does not always arrive with speed or spectacle, but often through systems that function continuously and invisibly, independent of whether we are aware of them. A sea snake does not need to see you to know you are there, because sight is only one way of knowing and not the most reliable one in a medium defined by flow. The final realization carried by the sea snake's hunting strategy is simple and unsettling. In water, you are never as anonymous as you think. Every movement leaves a trace. Every interaction with the environment writes a chemical sentence that can be read by the right predator. You may believe you are unseen, hidden by shadows or murk, but if you leave a trail, it can be followed, patiently and precisely, by an animal for whom the ocean is not just a place to swim, but a map written in scent. The reef feels open only until something begins to shape it, and few predators demonstrate this transformation as efficiently as the lionfish, an animal that does not rely on pursuit or brute force, but on turning three-dimensional space itself into a trap. In clear tropical water, where fish scatter easily and escape routes seem endless, the lionfish advances slowly, almost lazily, its ornate fins fanned wide like living architecture rather than anatomy. To an untrained eye, this display appears decorative, even wasteful, as though the animal were advertising vulnerability instead of danger. Yet within this apparent excess lies one of the most precise spatial hunting strategies on the reef, one that replaces speed with control and chaos with geometry. Lionfish occupy a unique sensory and physical niche, blending visual intimidation, fine-scale positioning, and behavioral manipulation into a system that preys not on individual weakness alone, but on the predictable responses of small reef fish under pressure. Their elongated pectoral fins, spread outward and forward, function not merely as appendages, but as barriers, creating a widening front that subtly redirects prey movement. Unlike predators that charge directly, forcing prey to scatter unpredictably, the lionfish advances at a measured pace, adjusting its orientation to guide fish away from open water and towards structural features such as coral heads, ledges, or rock faces. Each fin ray becomes part of a flexible fence, steering rather than chasing, shaping the environment until escape routes narrow and options collapse. This method works because reef fish, despite their agility, rely heavily on short bursts of speed and rapid turns to evade predators, strategies that require open space to be effective. When confronted by a predator that does not rush, but instead advances while blocking lateral movement, panic becomes counterproductive. Small fish attempt to dart sideways, only to encounter the looming curtain of spines and membranes, which they instinctively avoid due to both physical obstruction and the visual confusion created by the lionfish's high contrast patterning. Stripes, spines, and flowing fins disrupt depth perception, making it difficult for prey to judge distances accurately, and in moments of stress, misjudgment is fatal. The lionfish's sensory approach complements this physical manipulation. Rather than locking onto a single target and pursuing it relentlessly, the lionfish monitors the collective movement of prey, reading subtle shifts in direction and density. It makes micro-adjustments, slight rotations of the body, or incremental changes in fin angle to respond to these movements, maintaining pressure without overcommitting. This constant recalibration requires surprisingly little energy because the lionfish's body is buoyant and stable, allowing it to hover and pivot with minimal effort. The result is a predator that remains composed while its prey grows increasingly disorganized, expending energy rapidly as escape attempts fail. The final moments of the hunt are often anticlimactic in appearance, which is precisely why they are so effective. Once prey is herded into a corner or against a vertical surface, the lionfish closes the distance with a short, sudden suction strike, opening its mouth rapidly to draw in water and prey together. There is no dramatic lunge or extended chase, only a brief acceleration that capitalizes on proximity created through positioning rather than speed. The prey's panic has already done most of the work, exhausting escape options and compressing space until capture becomes inevitable. This strategy highlights a form of unfairness that is deeply unsettling from an ecological perspective because it exploits hardwired behaviors rather than outmatching physical ability. The lionfish does not need to be faster than its prey, only smarter in how it uses space. Its fins serve as both weapon and control system, simultaneously threatening, herding, and confusing, while venomous spines add an additional layer of deterrence that discourages counterattack by potential predators. Even larger fish that might otherwise challenge a slow-moving hunter think twice when confronted with a living array of spines capable of delivering painful, sometimes lethal stings. The reef itself becomes an accomplice in this process. Coral structures, often seen as refuges for small fish, transform into dead ends when approached from the wrong angle. The lionfish uses these features deliberately, positioning itself to cut off escape routes and funnel prey into predictable paths. What was once open habitat becomes a hallway with no exit, defined by the predator's body on one side and hard structure on the other. In this confined space, speed offers little advantage, and the very complexity that usually protects reef fish becomes a liability. From an energetic standpoint, this method is highly efficient. Lionfish expend far less energy per successful capture than many active hunters, allowing them to feed frequently without significant cost. This efficiency becomes particularly important when considering their impact in ecosystems where they are invasive, because it allows them to consume large numbers of prey without the natural checks imposed by energy limitations. Their ability to hunt effectively at all times of day, combined with a lack of evolved fear responses in native prey species, creates a scenario where containment-based predation can outpace the reproductive capacity of local fish populations. The sensory unfairness extends beyond physical containment to behavioral exploitation. Prey fish often rely on coordinated group movement to confuse predators, but the lionfish's approach fragments schools into smaller clusters, each easier to manage and isolate. As individuals peel away from the group in panic, they become targets not because they are slower or weaker, but because their behavior becomes more predictable. The lionfish reads this predictability, positioning itself to intercept paths of least resistance rather than chasing erratic movements. In this way, the predator benefits from fear itself, using panic as a tool rather than an obstacle. There is an almost architectural quality to this form of hunting, as if the lionfish were temporarily redesigning the reef to suit its needs. Space is divided, narrowed, and controlled through deliberate movement, turning an open environment into a series of constraints that favor the predator. This stands in contrast to hunters that rely on sudden bursts or surprise, because the lionfish announces its presence gradually, allowing prey to react in ways that ultimately seal their fate. The slow pace is not a flaw but a feature, maintaining control over the unfolding geometry of the encounter. Understanding this strategy also requires acknowledging the role of venom as a passive but critical component. While the venomous spines are rarely used actively during hunting, their presence reinforces the lionfish's dominance over space by discouraging interference. Potential competitors or predators that might disrupt the hunt avoid close contact, granting the lionfish uninterrupted control over its chosen area. This indirect protection allows it to focus entirely on manipulating prey movement without the need to remain vigilant for threats, further increasing efficiency. The broader ecological consequences of this hunting style are significant. By removing large numbers of small reef fish, lionfish alter the balance of herbivory and predation, affecting algae growth and coral health indirectly. Their success reshapes community structure not through sheer aggression, but through a method that scales easily with prey density and habitat complexity. Where reefs offer more structure, lionfish find more opportunities to create containment zones, amplifying their impact in precisely the environments most critical to reef resilience. From an evolutionary perspective, the lionfish represents a lesson in how morphology and behavior can converge to create dominance without speed. The elaborate fins, often dismissed as ornamental, are in fact multifunctional tools that integrate visual disruption, spatial control, and sensory feedback into a cohesive system. The fish's ability to maintain precise positioning in currents, to hover and pivot with minimal effort, and to interpret prey movement in real time reflects a level of specialization that challenges assumptions about what makes a predator effective. There is a subtle irony in how beautiful this system appears to human observers. The flowing fins, bold patterns, and calm demeanor draw admiration, masking the ruthless efficiency beneath. The lionfish does not look like a threat because it does not behave like one in familiar terms, and that disconnect mirrors the experience of its prey, which fails to recognize danger until containment is complete. Beauty, in this case, is part of the camouflage, reducing alarm and allowing the process to unfold uninterrupted. The final image left by the lionfish's hunting strategy is not one of speed or violence, but of inevitability. The reef narrows, movement options shrink, and panic accelerates the collapse of space until the outcome becomes unavoidable. There is no dramatic chase, no heroic escape, only a gradual realization that every path leads back to the same place. It is not speed that determines the kill, but containment, the quiet mastery of geometry that turns freedom into confinement and open water into a trap. The reef does not announce danger politely, and it rarely gives second chances. Yet among its inhabitants there exists a fish whose entire survival strategy is built not around escape or aggression, but around a single decisive refusal. The pufferfish does not outrun predators, does not overpower them, and does not stalk its meals with calculated precision, because its advantage lies elsewhere, in the ability to rewrite the rules of an encounter at the exact moment when those rules matter most. In a world where most predator-prey interactions are resolved through speed, stealth, or strength, the pufferfish survives by turning the act of capture itself into a catastrophic mistake. At rest, a pufferfish appears unremarkable, even vulnerable, drifting close to the reef or grazing slowly along coral and rock. Its movements measured and its body compact. It lacks the sleek lines of fast swimmers and the intimidating silhouettes of apex predators, and its small fins seem ill-suited for rapid escape. This apparent defenselessness is not accidental. It is the baseline state from which the pufferfish's defense becomes effective. Predators assess risk constantly, using size, shape, and behavior to determine whether an attack is worth the effort, and a relaxed, edible-looking fish sends the correct signal to trigger pursuit. The pufferfish does not advertise danger prematurely, because doing so would undermine the effectiveness of its transformation. The logic of inflation is brutally simple, yet evolutionarily elegant. Predators that hunt fish often rely on swallowing prey whole or manipulating it into a position where teeth and jaws can do their work. This requires a handling phase, a moment when the prey is restrained, oriented, and consumed. The pufferfish intervenes precisely at this stage, expanding its body rapidly by ingesting water or air, increasing its volume several times over in a matter of seconds. What was once a manageable bite becomes an awkward, rigid sphere, too large to swallow, difficult to grip, and suddenly dangerous to attempt consuming further. This transformation is not merely about size. It fundamentally alters the geometry of the encounter. Teeth designed to puncture or slice lose their effectiveness against a rounded, inflated surface, and jaws that rely on leverage struggle to find purchase. In many species, stiff spines protrude outward as the body expands, turning the pufferfish into a bristling object that threatens injury to the mouth and throat of any predator persistent enough to continue. The inflation does not need to be permanent or even prolonged. It only needs to last long enough to convince the attacker that the cost of continuing outweighs the benefit. What makes this defense particularly effective is that it is triggered neither too early nor too late. Pufferfish do not inflate at the first hint of danger, because unnecessary inflation is energetically costly and can draw attention rather than deflect it. Instead, they rely on a suite of sensory inputs to assess threat level, including vision, mechanoreception, and in some species, sensitivity to pressure changes and water movement. Subtle cues, such as the approach angle of a predator, changes in water flow caused by swimming motion, or sudden shadows overhead, inform the pufferfish's decision to deploy its primary defense. This assessment happens rapidly, allowing inflation to occur at the moment when capture is imminent, but not yet complete. From the predator's perspective, the experience is deeply disorienting. Sensory systems that have evolved to recognize prey by size, shape, and movement register a sudden and dramatic change that contradicts every expectation formed seconds earlier. The object that triggered the attack no longer fits the predator's internal model of food. Visual cues shift from edible to anomalous, tactile feedback becomes uncomfortable or painful, and in some cases, chemical cues associated with toxicity may begin to register as well. This sensory overload creates hesitation, and hesitation in a predator is often enough to break the sequence of attack, allowing the pufferfish to survive. The psychological dimension of this interaction is as important as the physical one. Predators learn through experience, and encounters that result in difficulty, discomfort, or injury are remembered and avoided in the future. A predator that attempts to consume a pufferfish and fails, especially if spines or toxins are involved, may permanently associate the puffer's appearance or behavior with risk, reducing the likelihood of future attacks not only on that individual, but on the species as a whole. In this way, the pufferfish's defense extends beyond the immediate moment, shaping predator behavior over time and reinforcing its effectiveness through learned avoidance. Toxicity adds another layer to this strategy, though it is not always immediately relevant during the inflation event itself. Many pufferfish species harbor potent toxins, such as tetrodotoxin, within their tissues, a substance that interferes with nerve function and can be lethal in sufficient doses. This toxin is not produced by the fish itself, but acquired through diet and symbiotic bacteria, making it another example of outsourced defense similar to the bioluminescent partnership seen in other marine animals. While a predator may not ingest enough toxin during a brief handling attempt to suffer immediate effects, the presence of chemical cues can reinforce the message that this prey is not worth the risk. The timing of inflation is critical because inflation restricts the pufferfish's own mobility and oxygen exchange, making prolonged inflation dangerous. Once expanded, the fish becomes less capable of active swimming and more vulnerable to secondary threats if the situation does not resolve quickly. Evolution has therefore fine-tuned the inflation response to be decisive but temporary, a short-lived state intended to interrupt the predator's attack rather than replace escape entirely. Once the threat has passed, the pufferfish gradually deflates, releasing water and returning to a more mobile form, often retreating into cover to recover. This balance between vulnerability and defense reflects a broader principle in reef ecology, where energy efficiency and risk management dictate survival strategies. Puffers are not constantly armored or aggressive because constant defense would be costly and unnecessary in an environment where threats vary in intensity and frequency. Instead, they invest in a rapid transformation that can be deployed when needed, conserving resources while maintaining a powerful deterrent. This approach allows puffers to occupy ecological niches where slow movement and deliberate foraging are viable, even in the presence of numerous predators. The sensory sophistication required to make this strategy work challenges assumptions about fish behavior and cognition. The pufferfish must integrate multiple streams of information to decide when inflation is appropriate, avoiding false positives that could waste energy or expose it to other risks. This decision-making is not conscious in the human sense, but it is the product of neural circuits shaped by selective pressure, capable of evaluating context and triggering complex physiological responses within moments. In this way, the pufferfish demonstrates that survival does not require intelligence as humans define it, but rather precise alignment between perception and response. The reef environment amplifies the effectiveness of this defense by providing structures that limit predator maneuverability. A predator attempting to handle an inflated puffer near coral or rock faces additional challenges, as space constraints reduce the ability to reposition or release the prey safely. This further increases the likelihood that the predator will abandon the attempt, reinforcing the puffer's advantage. Conversely, the puffer often positions itself near cover before or during inflation, ensuring that once released, it can retreat quickly to a safer location. There is an ironic elegance to the pufferfish's survival strategy because it relies on forcing the predator to confront its own limitations rather than exploiting weaknesses directly. Teeth, speed, and strength are rendered irrelevant by a sudden change in scale and shape, and the predator is left with a problem it did not anticipate. This inversion of power dynamics highlights a recurring theme in evolutionary biology, where success is often achieved not by competing on the same terms as others, but by changing the terms entirely. From a broader ecological perspective, pufferfish contribute to reef dynamics by influencing predator foraging patterns and behavior. Predators that learn to avoid puffers may shift their attention to other prey species, altering pressure on different populations and indirectly shaping community structure. In this way, the puffer's defense ripples outward, affecting interactions far beyond the immediate predator-prey encounter. The presence of puffers can therefore have stabilizing effects within reef ecosystems, distributing predation more evenly and preventing overexploitation of certain species. The human fascination with pufferfish often centers on their toxicity and unusual appearance. Yet these traits are only meaningful when viewed within the context of their ecological role. The true marvel lies not in the danger they pose to those who mishandle them, but in the precision with which they deploy their defenses in the wild. Inflation is not a panic response, but a calculated intervention, triggered at the moment when it will have maximum impact and minimum cost. The final impression left by the pufferfish is not one of aggression or fear, but of control exercised through refusal. Survival in this case is not about winning a fight or escaping at the last second, but about forcing the predator to stop, reassess, and retreat. The enemy's senses register food, then abruptly register error, and that shift is enough. In the relentless economy of the reef, where every encounter has a cost, the pufferfish survives by ensuring that touching it becomes a regret rather than a meal, a reminder that sometimes the most effective defense is not fighting back, but making the attack itself a mistake. The reef rarely feels intelligent in the way animals do, yet among its most unassuming inhabitants exists a form of perception so alien that it challenges the very definition of seeing. Sea urchins, those spiny spheres wedged into crevices or scattered across rock and sand, appear blind in every familiar sense, lacking eyes, lenses, pupils, or any centralized visual organ that resembles sight as humans understand it. They do not track movement with a gaze, do not swivel toward threats, and do not scan their surroundings in any obvious way. And yet, they respond to light with startling accuracy, retreating from exposure, orienting toward shadow, and navigating complex reef structures with a consistency that cannot be explained by touch or chance alone. The truth is unsettling and elegant at the same time. A sea urchin does not see with eyes, because its entire body functions as one. To understand how this is possible, the perspective must shift away from faces and towards surfaces, because the sea urchin is built not around a head, but around a sphere of coordinated sensory units. Its body is covered in tube feet, flexible appendages that extend and retract through small openings in the shell, driven by hydraulic pressure and controlled with surprising precision. These tube feet are best known for locomotion and adhesion, allowing the urchin to grip rock, climb vertical surfaces, and resist powerful waves. But hidden within their tissue are photoreceptor cells capable of detecting light. Individually, these cells provide only crude information, unable to form images or resolve detail. Yet collectively, they create a distributed sensory network that allows the animal to perceive changes in brightness and direction across its entire surface. This distributed vision system operates more like a biological mosaic than a camera, with each tube foot sampling light independently and feeding that information into a nervous system that integrates the signals into a functional response. When light increases on one side of the body, tube feet on that side detect the change, triggering movement away from exposure. When shadow falls unevenly, the imbalance guides the urchin toward darker areas. The result is not sight in the pictorial sense, but spatial awareness grounded in light gradients rather than images. In effect, the sea urchin experiences the world as a shifting pattern of brightness mapped directly onto its body, a sensation that feels more like inhabiting a sensor array than possessing a viewpoint. The implications of this system become clear when observing how sea urchins behave in exposed environments. On open reef flats or shallow rocky shores, intense sunlight increases the risk of desiccation, overheating, and predation, making exposure dangerous despite the apparent protection offered by spines. Urchins respond by moving deliberately towards shaded crevices, overhangs, or deeper water, not randomly, but with directional consistency that reflects an ability to compare light levels across space. Even without eyes, they choose safer positions, often clustering in shadowed areas during peak daylight hours and emerging to graze when light levels drop. This behavior cannot be explained by chance or purely tactile exploration, because the decisions occur before physical contact with shelter is made. The reef itself amplifies the usefulness of this perception. Light underwater is fractured by surface waves, filtered by depth, and distorted by suspended particles, creating a complex mosaic of brightness and shadow that shifts constantly. For visually oriented animals, this complexity can obscure threats or opportunities, but for an organism tuned to gradients rather than shapes, it provides a rich source of information. The sea urchin does not need to identify predators visually. It only needs to recognize conditions associated with increased risk, such as open, brightly lit areas where cover is scarce. By responding to light rather than specific objects, it avoids exposure in a way that is broadly effective across different habitats and predator communities. This form of perception also helps explain the sea urchin's role as a powerful ecological engineer. Urchins are voracious grazers, capable of stripping algae from rock surfaces and reshaping reef landscapes over time. Their movement patterns, guided in part by light detection, determine where grazing pressure is concentrated. In shaded or deeper areas, urchins may feed more aggressively, while exposed zones experience reduced grazing due to avoidance behavior. This creates patchy landscapes where algae and corals compete differently, depending on light exposure and urchin activity, influencing the distribution of species across the reef. The urchin's crude vision, therefore, has consequences that extend far beyond its own survival. The sci-fi quality of this system becomes even more apparent when considering how it differs fundamentally from centralized sensory processing. Most animals evolve to concentrate sensory organs in a head, creating a forward-facing interface that allows rapid interpretation and reaction. The sea urchin abandons this model entirely, distributing perception across the body in a way that eliminates the concept of front and back. There is no single point of vulnerability, no critical organ that can be damaged to blind the animal completely. Instead, perception is redundant, resilient, and persistent, functioning as long as enough tube feet remain operational. This decentralization reflects a survival strategy shaped by life in environments where damage is common and regeneration is possible. Indeed, regeneration is a key companion to distributed sensing. Sea urchins can regrow spines and tube feet lost to predation or environmental stress, restoring not only physical structure but sensory capacity. Because perception is spread across many units, the loss of a few does not cripple the animal's ability to detect light. This resilience reinforces the effectiveness of the system over evolutionary time, favoring organisms that can endure damage without catastrophic loss of function. In a reef ecosystem filled with biting, crushing, and scraping predators, this ability to absorb injury while maintaining awareness is a powerful advantage. The lack of eyes also challenges assumptions about intelligence and complexity. Sea urchins are often dismissed as simple or primitive, yet their sensory system represents a sophisticated solution to environmental challenges, one that trades resolution for reliability. They do not need to recognize specific predators or navigate intricate paths with precision. They need to make consistent decisions about exposure and shelter, and light detection is sufficient for that task. This efficiency reflects a broader principle in evolution, where success depends not on maximizing capability, but on matching capability to need. There is a quiet irony in how unsettling this form of vision feels to human observers. Eyes are familiar, readable, and expressive, allowing us to infer intent and awareness in other animals. A creature that sees without eyes disrupts that intuition, creating a sense of unease rooted in unfamiliarity rather than threat. The sea urchin does not look back, yet it responds, retreats, and positions itself with purpose, reminding us that perception does not require a face, only a means of detecting change and acting upon it. This system also influences how predators interact with sea urchins. Many predators rely on visual cues to assess prey vulnerability, and the absence of obvious eyes or reactive behavior can make urchins difficult to read. Combined with their spines and, in some species, chemical defenses, this ambiguity reduces predation pressure, allowing urchins to persist even in heavily hunted environments. Predators that do attack must contend not only with physical defenses, but with an animal that can reposition itself to reduce exposure before contact occurs, guided by light cues that signal danger indirectly. The distributed vision of sea urchins also blurs the boundary between sensing and movement. Tube feet do not merely detect light, they are also the means by which the animal responds, extending, retracting, and gripping in coordinated patterns that shift the body's position. Perception and action are tightly coupled, reducing the delay between stimulus and response. When light levels change, the same structures that detect the change initiate movement, creating a feedback loop that feels less like decision-making and more like continuous adjustment. This integration further enhances survival by minimizing reaction time without requiring complex processing. From a broader evolutionary perspective, the sea urchin's sensory strategy highlights how diverse solutions can emerge to the same fundamental problem: knowing where you are in relation to danger. While eyes evolved to provide detailed images in many lineages, other organisms found ways to extract just enough information from their environment to make effective choices. In the sea urchin's case, light detection without image formation proves sufficient to navigate a world where exposure matters more than detail. This challenges the assumption that more information is always better, suggesting instead that the right information, even if crude, can be enough. The reef, seen through this lens, becomes not just a visual spectacle, but a field of gradients constantly interpreted by organisms in ways invisible to us. Brightness, shadow, and contrast guide movement and behavior across species, shaping interactions that unfold silently and continuously. The sea urchin participates fully in this sensory dialogue, despite lacking the organs we associate with perception, reminding us that the reef is read as much as it is seen. The final impression left by the sea urchin is one of quiet strangeness rather than menace. Here is an animal that perceives without eyes, reacts without a face, and navigates without a viewpoint, embodying a form of awareness that feels more like environmental immersion than observation. It does not look out at the world. It feels light across its entire body and moves accordingly. In doing so, it reveals an unsettling truth about perception itself. Sometimes the creepiest vision does not come from eyes at all, but from an organism that turns its whole body into a way of seeing. The seafloor does not announce itself with clear edges or visible paths, especially once light fades and suspended particles turn water into a shifting haze. Yet for lobsters, this apparent confusion is not an obstacle, but a richly annotated map. Where human senses fail almost immediately, overwhelmed by darkness or turbidity, lobsters move with confidence, navigating a world defined not by sight, but by chemistry. Every current carries information, every surface holds residue, and every movement leaves a molecular signature that can be detected, interpreted, and followed with remarkable precision. To understand a lobster is to abandon the idea that navigation requires vision, because for this animal, smell is not a secondary sense, but the primary language through which the environment is read. A lobster's body is built to receive chemical information from nearly every direction. But the most obvious tools are its long antennae, which extend forward like probing instruments, sweeping through the water and sampling dissolved molecules with each slow, deliberate motion. These antennae are densely packed with chemoreceptors, capable of detecting extremely low concentrations of compounds associated with food, conspecifics, predators, and suitable shelter. Unlike vision, which requires line of sight and sufficient light, chemical detection works around corners, through darkness, and across distances shaped by currents rather than geometry. A dead fish hidden behind rocks, a rival lobster occupying a nearby crevice, or a safe den emitting familiar chemical cues can all be detected without direct contact, allowing the lobster to make informed decisions before committing to movement. This sensory system transforms the ocean into a gradient-based landscape, where concentration differences guide behavior much like elevation guides movement on land. Lobsters do not wander aimlessly across the sea floor, hoping to stumble upon food or shelter. They orient themselves along chemical gradients, moving from areas of lower concentration toward higher ones in a process that resembles tracking more than searching. This behavior is especially evident at night, when lobsters emerge from shelters to forage under cover of darkness, relying almost entirely on chemical cues to navigate. The direction of movement is not random, but adjusted continuously as antennae sample the water, comparing inputs from left and right to determine the direction of strongest signal. The effectiveness of this strategy depends on the physics of water itself, which carries dissolved chemicals in predictable patterns shaped by currents, turbulence, and contact with surfaces. While air disperses scent rapidly and unpredictably, water preserves chemical trails for longer periods, allowing them to stretch and bend without disappearing entirely. A lobster following such a trail is not tracing a straight line, but interpreting a complex plume that widens, narrows, and shifts as it moves downstream. This requires constant adjustment, with the lobster slowing, pausing, or changing direction as sensory input fluctuates, demonstrating a level of environmental reading that goes far beyond simple attraction to smell. What makes this system even more remarkable is that chemical sensing in lobsters is not confined to the antennae. The walking legs themselves are equipped with chemoreceptors, allowing the animal to taste the environment through direct contact with the substrate. Each step becomes a sampling event, gathering information about what has passed over the ground recently and what lies ahead. This ability turns movement into exploration as the lobster integrates information from waterborne cues above and contact cues below, creating a layered understanding of its surroundings. Touching the seafloor is not just locomotion, it is another way of reading the chemical story written into the environment. This distributed sensing is particularly useful in complex habitats such as rocky reefs, kelp forests, and debris fields, where visual navigation would be unreliable even in daylight. Lobsters use chemical cues to locate and evaluate shelters, often preferring dens that carry familiar scents, indicating previous occupation or proximity to food sources. These shelters become central nodes in their spatial memory, places that are revisited repeatedly and defended against rivals. Chemical communication plays a critical role here because lobsters can detect the presence of other individuals through scent alone, assessing size, sex, and dominance without direct confrontation. This reduces unnecessary conflict and allows social hierarchies to form around shelters and feeding areas. The role of chemical sensing in lobster behavior becomes even more apparent during interactions with conspecifics. Lobsters release chemical signals that convey information about dominance, reproductive status, and territorial claims, shaping encounters before physical contact occurs. A lobster approaching a den can detect whether it is occupied and by whom, deciding whether to retreat, challenge, or attempt to negotiate access through ritualized displays. These decisions are informed by scent rather than sight, because in the tight confines of a rocky crevice, chemical information travels more reliably than visual cues. The result is a social system mediated largely through invisible signals, where outcomes are often decided before claws are raised. Food detection follows a similar pattern, with lobsters responding to the chemical signatures of decaying organic matter, injured prey, or active organisms that release metabolic byproducts into the water. A lobster can locate a food source from considerable distance if currents carry the scent toward it, adjusting its path as conditions change. This ability allows lobsters to exploit ephemeral resources efficiently, arriving at carrion or feeding opportunities soon after they appear. In ecosystems where competition is intense and food availability unpredictable, speed of detection matters more than speed of movement, and chemical sensing provides that advantage. The dominance of chemical perception also explains why lobsters remain effective hunters and scavengers in environments that defeat visually oriented predators. In murky water, at night, or beneath thick kelp canopies, eyesight offers limited guidance, but chemical cues remain intact. Lobsters do not need to see prey clearly to find it. They only need to follow the trail left behind. This makes them particularly resilient to changes in visibility caused by storms, sediment runoff, or seasonal plankton blooms, allowing them to maintain consistent foraging success even when other species struggle. Thermoregulation and seasonal movement further interact with this sensory world because temperature affects both lobster physiology and chemical dispersion. Lobsters are ectothermic, relying on environmental heat to regulate metabolism, which influences activity levels and sensory sensitivity. In colder water, chemical signals disperse differently and metabolic rates slow, altering how lobsters interpret and respond to cues. Seasonal migrations, such as movements to deeper water during colder months, are guided not only by temperature gradients, but by the persistence of familiar chemical landscapes that indicate suitable habitat. In this way, smell becomes a long-term navigational aid, reinforcing routes and destinations across time. The evolutionary implications of this sensory dominance are profound, because they demonstrate how different solutions can emerge to the same ecological challenges. Where many animals evolved sharper vision or faster movement, lobsters invested in chemical literacy, becoming experts at reading the molecular language of the sea. This choice reflects the constraints and opportunities of their environment, where hard substrates, low light, and complex structures favor sensing systems that do not depend on clear lines of sight. Over millions of years, selection refined antennae, legs, and neural pathways into a cohesive system capable of extracting meaning from chemical noise. Human interactions with lobsters inadvertently reveal just how powerful this system is. Baited traps exploit the lobster's reliance on scent, drawing individuals from surrounding areas through chemical attraction alone. The success of such traps underscores the extent to which lobsters trust chemical cues as indicators of opportunity, often prioritizing them over caution. At the same time, it highlights a vulnerability, because the same sensory pathways that guide lobsters efficiently in natural settings can be manipulated in artificial ones. This interaction serves as a reminder that specialization, while advantageous, can carry costs when environments change rapidly. Despite this vulnerability, lobsters remain remarkably adaptable, adjusting behavior in response to altered chemical landscapes created by human activity. Pollution, changes in water chemistry, and habitat modification can disrupt scent trails. Yet lobsters often compensate by relying more heavily on contact chemoreception through their legs and antennae, maintaining functional navigation even under degraded conditions. This flexibility suggests that while chemical sensing dominates, it is not monolithic, but integrated with other senses to create a robust perception system capable of absorbing disruption. The idea that the ocean is filled with trails may feel abstract until one considers how constantly organisms shed chemical information. Every breath, every movement, every interaction with the substrate releases molecules into the water, creating a continuous record of presence and activity. Lobsters live immersed in this record, interpreting it moment by moment as they move through their environment. Where humans see empty space, lobsters perceive gradients, intersections, and destinations, navigating a world that is richly structured even when invisible. This sensory perspective reframes the seafloor as a dynamic information network, rather than a static landscape. Rocks are not just obstacles but reservoirs of scent. Currents are not just forces but conveyors of meaning. And darkness is not absence but a condition under which chemical information becomes even more valuable. Lobsters thrive in this network, not by overpowering or outpacing others, but by understanding how information flows through water and positioning themselves accordingly. The final realization left by the lobster's world is both simple and transformative. The ocean is never blank, even when it appears so to human eyes. It is layered with trails that persist, overlap, and fade, carrying stories of movement, conflict, and opportunity. Lobsters do not stumble through this complexity. They read it, step by step and flick by flick, following chemical sentences written into the water itself. In a realm where vision falters and sound dissipates, smell becomes navigation, and survival belongs to those who know how to follow what the ocean leaves behind. The reef does not forgive ignorance, because complexity punishes hesitation as efficiently as it rewards understanding. And few fish embody this balance between brute force and cognition as clearly as the Napoleon fish. Known for its massive head, thick lips, and almost prehistoric bulk, this is an animal that initially reads as a moving wall rather than a thinker, a creature whose success appears rooted purely in size and jaw strength. Yet that first impression dissolves the longer one observes how it moves through reef space, because the Napoleon fish is not wandering, not reacting randomly to stimuli, and not simply biting whatever crosses its path. It patrols, revisits, and selects, operating with a level of spatial awareness that turns the reef from a chaotic maze into a memorized territory shaped by routine and recognition. Coral reefs are among the most structurally complex ecosystems on the planet, packed with vertical relief, overhangs, tunnels, and microhabitats that constantly shift with growth, erosion, and biological activity. For small fish, survival often depends on instant reactions and tight shelter use. But for a giant like the Napoleon fish, survival depends on knowing where to go and when. Its size limits access to many hiding places, and its slow cruising speed rules out high-energy pursuit, forcing a different strategy altogether. The detection problem for this fish is not spotting prey on the move, but identifying where worthwhile prey lives, where defenses can be overcome, and which areas are worth returning to again and again. The jaws of the Napoleon fish are legendary for good reason. Thick bone, reinforced musculature, and crushing teeth allow it to consume prey that is inaccessible to most reef predators, including hard-shelled mollusks, crustaceans, and even echinoderms protected by armor or spines. This ability opens an entire category of food sources that are effectively invisible to other fish, not because they cannot be seen, but because they cannot be processed. The reef is filled with organisms that survive by being unpalatable rather than fast, and the Napoleon fish ignores that contract entirely, treating defensive shells as inconveniences rather than barriers. But crushing power alone does not explain efficiency, because indiscriminate biting would waste time and energy on low-reward targets. Instead, the Napoleon fish behaves like an informed forager, moving through the reef along routes that appear habitual rather than exploratory. Individuals have been observed following consistent patrol paths, visiting the same bommies, ledges, and coral heads over extended periods, suggesting a memory-based understanding of where productive feeding sites exist. This behavior implies spatial mapping, the ability to remember not just locations, but outcomes, distinguishing between areas that reliably produce food and those that do not. In a reef environment where prey populations fluctuate and regrow over time, returning too frequently to the same site could deplete resources, while returning too late risks losing them to competitors. Timing, therefore, becomes as important as location. This is where cognition becomes inseparable from physical dominance. The Napoleon fish does not need to rush. because its advantage is not speed, but certainty. It approaches a site already knowing what it is likely to find there, scanning surfaces and crevices with deliberate movements rather than frantic searching. When it engages prey, it does so decisively, crushing and consuming in a few powerful motions, then moving on rather than lingering. This efficiency minimizes exposure to parasites, reduces energy expenditure, and allows the fish to maintain a wide patrol range without exhausting local food sources. The reef responds to this presence in subtle ways. Prey species that rely on armor rather than mobility often position themselves in areas where Napoleon fish patrols are infrequent, shifting distribution patterns based on learned risk. Over time, this creates a spatial dialogue between predator and prey, where movement and settlement patterns reflect not just physical defenses, but cognitive anticipation. The Napoleon fish, in turn, adapts its routes as these distributions change, reinforcing the role of memory and learning in shaping feeding success. Recognition extends beyond prey to the structure of the reef itself. Coral formations change slowly, but storms, bleaching events, and biological erosion can alter passageways and feeding sites enough to matter. A fish that relies solely on instinctive responses would struggle to adapt, but the Napoleon fish appears capable of updating its internal map, adjusting routes and revisiting areas that have changed. This flexibility is crucial in an ecosystem as dynamic as a reef, where yesterday's shelter can become today's rubble and new opportunities emerge unpredictably. The social dimension adds another layer to this intelligence. Napoleon fish are not schooling fish in the traditional sense, but they do interact with conspecifics in ways that suggest recognition and hierarchy. Large individuals often dominate prime territories, while smaller ones occupy peripheral areas, and these arrangements can persist over time. Such stability implies an ability to recognize individuals, or at least assess familiar patterns of presence, reducing constant conflict and allowing energy to be invested in feeding rather than fighting. Again, memory acts as a force multiplier, amplifying physical advantage through reduced uncertainty. Detection, in this context, becomes less about acute sensory thresholds and more about informed expectation. The Napoleon fish does not need exceptional eyesight to spot prey if it already knows where prey is likely to be. Vision still plays a role, of course, allowing it to assess condition and positioning, but the heavy lifting is done by experience accumulated over repeated patrols. The reef becomes readable not through moment-to-moment sensory overload, but through familiarity, a place where each turn and crevice carries a history of success or failure. This approach stands in contrast to many reef predators that rely on ambush or burst speed, strategies that demand constant readiness and high energy output. The Napoleon fish invests instead in learning, allowing it to move slowly and deliberately through its environment while maintaining high feeding efficiency. This strategy is particularly effective for a large-bodied fish because it reduces unnecessary exertion and lowers risk, important factors for an animal that cannot easily hide or flee. The idea that a fish can learn routes, remember locations, and adjust behavior based on past outcomes challenges outdated assumptions about intelligence in marine animals. While the Napoleon fish does not solve puzzles or use tools in the human sense, its success depends on integrating spatial memory, pattern recognition, and physical capability into a coherent strategy. This integration allows it to exploit the reef in ways that pure strength or pure speed never could, reinforcing the idea that intelligence in nature is task-specific rather than universal. The reef itself reinforces this lesson because complexity favors organisms that can navigate it mentally as well as physically. Labyrinthine habitats punish randomness and reward familiarity, turning memory into a survival trait. Animals that succeed here are not always the fastest or most aggressive, but those capable of learning where danger and opportunity intersect. The Napoleon fish thrives because it treats the reef not as a battlefield to be conquered, but as a system to be understood. There is a quiet authority in how it moves, a sense that each patrol is purposeful rather than exploratory, each stop deliberate rather than curious. This demeanor can be mistaken for indifference, but it reflects confidence built on knowledge. The fish does not rush because it does not need to, and it does not hesitate because it already knows what comes next. Strength ensures it can take what it finds, but memory ensures it finds what is worth taking. From an ecological perspective, this behavior has far-reaching effects. By consuming hard-shelled prey, the Napoleon fish influences population balances that would otherwise remain unchecked, preventing certain species from dominating reef surfaces. Its selective feeding helps maintain diversity, opening space for coral growth and other organisms that compete with armored invertebrates. In this way, its intelligence and strength combine to shape the reef's structure, making it not just a predator, but a regulator. The final realization offered by the Napoleon fish is deceptively simple. Power alone is rarely enough in complex environments. The reef does not reward the fish that hits hardest or moves fastest, but the one that understands where to go, when to return, and what is worth the effort. In a world of endless hiding places and shifting opportunity, learning becomes a form of dominance, and memory becomes as important as muscle. The reef, in the end, rewards the fish that can learn. The shallow coastal sea rarely feels dramatic in the way open ocean or reef edges do. Yet for a dugong, it is a landscape every bit as complex, dangerous, and information-rich as any predator arena. This is not a place of speed or spectacle, but of subtle gradients, shifting sandbanks, and meadows that appear and disappear with tides, storms, and seasons. To survive here is not about chasing or striking, but about knowing where nourishment persists, how to reach it safely, and how to remain unobtrusive in waters crowded with threats that do not need to hunt actively to be lethal. The dugong moves through this environment with a calm that looks like simplicity, but beneath that calm lies a refined sensory strategy tuned to endurance rather than confrontation. Seagrass is not evenly distributed across the seafloor, nor is it static. Meadows grow where light penetrates shallow water, where sediment remains stable enough for roots to anchor, and where nutrient flow supports slow but steady growth. These conditions shift constantly. A single storm can bury a meadow under sand, uproot plants entirely, or expose new growth elsewhere. Tides reshape channels, currents rearrange sediment, and grazing itself alters the structure of the bed. For an animal whose entire diet depends on this fragile habitat, feeding is not a matter of drifting until something green appears, but of navigation, memory, and selection refined over years. Dugongs do not graze indiscriminately. They favor particular seagrass species, often selecting younger, more nutritious shoots and returning repeatedly to areas where regrowth is reliable. As they feed, they leave behind distinctive trails, long furrows carved into the sediment where roots have been uprooted and consumed. These feeding paths are not signs of destruction alone, but of interaction, because grazing stimulates regrowth in many seagrass species, encouraging fresh shoots that can be more nutritious than untouched plants. Over time, dugongs reshape meadows into patchwork landscapes, where grazed and ungrazed areas alternate, influencing plant diversity, sediment stability, and the distribution of other species that depend on seagrass for shelter. This feedback loop turns the environment itself into a source of information. A dugong returning to a familiar feeding ground is not encountering an unknown space, but reading a living record of past activity, including its own. The texture of the sediment, the density of regrowth, and the arrangement of feeding trails all signal whether an area is worth revisiting or should be left to recover. This reliance on familiarity suggests a strong role for spatial memory, because wandering randomly across shallow coastal waters would be inefficient and dangerous. Dugongs move slowly, surface regularly to breathe, and cannot afford unnecessary exposure to boat traffic, predators, or shallow obstacles. Vision plays a role in this world, but it is often compromised by turbidity, glare, and suspended sediment stirred up by tides and feeding itself. In such conditions, other senses take on greater importance. Sound travels efficiently in shallow water, carrying information about approaching disturbances long before they are visible. A dugong can detect the low-frequency noise of a boat engine, the turbulence created by waves breaking over a sandbank, or the subtle changes in ambient sound that signal shifting tides. These auditory cues help the animal adjust its movement, choose when to surface, and decide whether to remain in an area or retreat to deeper, quieter water. Smell also contributes to this sensory map, not in the dramatic tracking sense seen in predators, but as a background layer of information that helps identify suitable habitat. Seagrass releases chemical compounds into the water, and sediment carries the scent of organic matter, decay, and renewal. While dugongs do not follow trails like hunting animals do, they are immersed in a chemical environment that reflects the health and productivity of the meadow. Familiarity with these cues, built through repeated use of the same feeding grounds, reinforces navigation choices and reduces the need for constant exploration. Touch, perhaps more than any other sense, anchors the dugong to its environment. The flexible, muscular snout is adapted to uproot seagrass efficiently, but it is also a sensitive organ that reads the texture of the substrate. Sand that shifts too easily signals instability, while compacted sediment suggests established root systems worth grazing. As the dugong feeds, it feels its way through the meadow, adjusting pressure and angle to maximize intake while minimizing effort. This tactile feedback becomes part of the decision-making process, guiding how long the animal remains in one place and when it moves on. Thermoregulation adds another dimension to this sensory balance. Dugongs are sensitive to cold, relying on warm, shallow waters to maintain body temperature. Seasonal changes influence not only where seagrass grows, but where dugongs can feed comfortably. During colder periods, they may seek deeper channels with slightly warmer water, or migrate to regions where temperatures remain stable. These movements are not random migrations across vast distances, but targeted shifts guided by knowledge of coastal geography, water temperature patterns, and the availability of feeding grounds. Again, memory and familiarity play critical roles, because finding suitable habitat quickly can mean the difference between maintaining energy balance and suffering thermal stress. Predation pressure, though less obvious than in the lives of sharks or rays, shapes dugong behavior continuously. While adult dugongs have few natural predators, calves are vulnerable, and both are at risk from human activity. The strategy here is not evasion through speed, but avoidance through predictability and restraint. Dugongs often follow established routes between feeding and resting areas, moving slowly and consistently rather than darting unpredictably. This reduces noise, limits sediment disturbance, and minimizes attention. In shallow coastal waters, being unnoticed can be more valuable than being fast. The calm demeanor that defines the dugong is therefore not passivity, but an adaptation to an environment where constant vigilance would be unsustainable. Energy must be conserved, stress minimized, and exposure controlled. Sensory input is filtered not for immediate threat detection alone, but for long-term patterns that support survival over decades. Dugongs are long-lived animals, and their strategies reflect this lifespan, favoring caution, consistency, and environmental understanding over short-term gain. The reshaping of seagrass beds through feeding has broader ecological consequences that underscore the dugong's role as more than a quiet grazer. By creating feeding trails and patchiness, dugongs influence sediment oxygenation, nutrient cycling, and the distribution of invertebrates and fish that use seagrass as habitat. This engineering effect can increase biodiversity within meadows, preventing any single species of seagrass from dominating and promoting resilience against disturbance. In this way, the dugong's sensory-driven feeding behavior contributes to ecosystem stability, even as it satisfies individual nutritional needs. There is an irony in how easily this complexity is overlooked. From a distance, a dugong drifting over a seagrass bed appears almost inert, moving slowly, surfacing gently, and disappearing again beneath the water. Yet every movement reflects a series of decisions informed by sound, touch, chemical familiarity, and memory. The animal is constantly negotiating trade-offs between feeding efficiency, safety, and energy conservation, using senses not to dominate its environment, but to coexist within it. This perspective broadens the theme of sensing beyond predation and conflict, revealing how perception underpins survival even in the absence of active threat. Dugongs do not hunt, but they must still detect, choose, and avoid. Their world is quieter, but not simpler, shaped by gradients rather than targets, and by routes rather than pursuits. The same sensory principles that allow predators to intercept prey allow dugongs to intercept opportunity and avoid danger without confrontation. Understanding dugongs in this way challenges the assumption that sensory sophistication is reserved for aggressive or highly mobile animals. In reality, any organism that depends on a dynamic environment must develop ways to read it accurately. For dugongs, this reading is gentle and cumulative, built through repeated interaction with the same landscapes over years. The seagrass meadow becomes not just a feeding ground, but a familiar space imbued with meaning, history, and expectation. The final impression left by the dugong is one of quiet intelligence rather than power. This is an animal that survives not by being feared, but by knowing when and where to exist. Its senses are tuned not for attack, but for persistence, allowing it to navigate a fragile coastal world without drawing attention. In an ocean often defined by predators and violence, the dugong reminds us that survival can also mean blending in, moving carefully, and shaping the environment gently enough to remain part of it. The sea is not only a battlefield of hunters and hunted, it is also a place where some animals endure by learning how not to be found. The seafloor often feels like the safest place to rest, a realm of stillness where danger appears slow, obvious, and avoidable. Yet this sense of security dissolves once the rules of predation are understood beyond speed and teeth. Starfish, or sea stars, do not chase, do not ambush, and do not strike in the ways most predators do, which is precisely why they are so effective. They represent a form of hunting that feels almost passive, yet unfolds with a certainty that makes escape irrelevant once the process has begun. In an ecosystem where motion usually signals threat, the starfish succeeds by doing the opposite, advancing slowly, guided not by sight or aggression, but by chemistry and inevitability. At first glance, a starfish appears poorly equipped for predation. It lacks a centralized brain, has no jaws, no obvious sensory organs, and moves at a pace that would seem laughable in open water. Yet this simplicity is misleading, because its body is built around a distributed sensory and digestive system that excels in environments where prey cannot flee easily. Starfish inhabit substrates where many organisms rely on concealment rather than speed for protection, burying themselves in sand, sealing themselves within shells, or anchoring to rock. These defenses are effective against predators that rely on vision or pursuit, but they fail against one that can detect prey chemically and consume it without needing to overpower it conventionally. The starfish lives in a chemical landscape, much like lobsters and other benthic organisms, but with a different purpose. Its tube feet, which line the undersides of its arms, are not merely tools for locomotion and adhesion. They are also sensitive to dissolved chemical cues released by potential prey. Bivalves, barnacles, and other sessile or slow-moving animals constantly leak molecular traces into the water as they respire, feed, and excrete waste. These chemical signatures disperse across the seafloor, forming gradients that persist even when prey is buried or tightly sealed. The starfish reads these gradients not as vague hints, but as directional information, allowing it to orient toward food sources that remain completely invisible. This ability fundamentally changes what it means to hide. A mussel clamped shut within its shell, or a clam buried beneath sand is visually secure, but chemically exposed. The starfish does not need to see its prey, or even touch it initially. It only needs to detect the gradient and follow it. Movement is slow, but it is purposeful, with each arm contributing to a coordinated advance guided by the strongest chemical signal. Over time, this movement brings the starfish into direct contact with prey that believed itself unreachable, transforming concealment into a false sense of safety. Once contact is made, the encounter shifts into a form of predation that feels almost alien in its execution. Starfish do not rely on biting or tearing, because their feeding strategy bypasses the need to open shells or breach defenses through force alone. Instead, many species employ a method that is both biologically efficient and unsettling in its intimacy. The starfish everts its stomach, pushing it out through its mouth and into the shell or cavity of the prey. Digestive enzymes are released externally, breaking down soft tissues while the prey is still alive, allowing nutrients to be absorbed before the stomach is retracted back into the body. This process eliminates the need for speed, strength, or precision strikes. A tightly sealed shell becomes irrelevant when digestion occurs outside the predator's body. The prey's defenses, evolved to prevent entry, offer no protection against a predator that consumes from the outside in. The starfish does not need to win a struggle. It only needs to maintain contact long enough for chemistry to do the work. This makes predation slow, but once initiated, extremely difficult to stop. The sensory component of this strategy is crucial because the starfish cannot afford to waste time on unsuitable targets. External digestion is energetically expensive, and prolonged exposure increases vulnerability to disturbance. Chemical detection allows the starfish to assess prey suitability before committing fully, responding more strongly to cues associated with nutrient-rich organisms and ignoring weaker signals. In this way, sensing and feeding are tightly integrated, ensuring that effort is directed where payoff is likely. From the prey's perspective, this encounter is not dramatic, but insidious. There is no sudden attack, no moment of realization marked by impact or pursuit. Instead, the threat arrives gradually, often unnoticed until it is too late. A bivalve may detect pressure changes as the starfish settles atop it, but by then, escape is unlikely. The starfish's tube feet create a powerful grip, using hydraulic pressure to maintain position despite attempts to pry free. Over time, muscle fatigue sets in, shell gape widens slightly, and the external stomach gains access, sealing the outcome through biochemical means rather than physical dominance. This style of predation has profound ecological implications because it targets organisms that form the structural foundation of many benthic communities. Bivalves and other sessile animals filter water, stabilize sediment, and create habitat for countless smaller species. By preying on them, starfish regulate population densities, preventing any single species from monopolizing space and resources. In some ecosystems, changes in starfish abundance can trigger cascading effects, reshaping entire communities through shifts in competition and habitat availability. The slow predator, in this case, becomes a powerful architect of ecosystem structure. The starfish's lack of centralized control further reinforces its eerie effectiveness. Its nervous system is decentralized, allowing each arm to respond semi-independently to sensory input while remaining coordinated with the whole. This means that damage to one part of the body does not incapacitate the animal entirely. Some species can even regenerate lost arms, turning injury into a temporary setback rather than a fatal event. This resilience complements the slow, methodical nature of their hunting strategy, allowing starfish to persist in environments where disturbance is common and recovery is essential. Temperature and environmental conditions further shape this predatory process. As ectotherms, starfish rely on ambient temperatures to regulate metabolic rate, influencing how quickly digestion occurs and how long feeding can be sustained. In warmer conditions, digestion accelerates, reducing the time needed to extract nutrients, while colder water slows the process, extending exposure. Starfish adjust behavior accordingly, often selecting feeding times and locations that balance energy gain against risk, demonstrating an interaction between physiology and sensory-guided decision-making. The unsettling aspect of starfish predation lies not in violence, but in patience. This is a predator that does not rush, does not tire easily, and does not abandon its target once engaged. Escape is possible only before contact is made, which places enormous importance on early detection for prey species. Yet many prey are evolutionarily tuned to detect rapid movement or mechanical disturbance, not slow chemical approach. This mismatch gives starfish a persistent advantage, allowing them to exploit a blind spot in the defensive strategies of other organisms. There is a quiet horror in realizing that predation does not require intent or aggression as humans understand it. The starfish follows chemical cues because that is how it feeds, not because it chooses to harm. Its slow advance feels indifferent rather than malicious, making the outcome feel inevitable rather than contested. This challenges the narrative of predator and prey as a dynamic contest, replacing it with a model where time itself becomes the weapon. From a sensory perspective, the starfish exemplifies how perception does not need to be sharp to be effective. It does not see prey clearly, nor does it react quickly, but it senses reliably. Chemical cues do not disappear suddenly, and as long as the gradient exists, the starfish can follow it. This persistence ensures that escape through stillness or concealment remains unreliable, especially for organisms that cannot relocate quickly. Slow movement becomes irrelevant when the predator never loses the trail. As the episode closes, the starfish reframes the entire theme of sensing and survival. Here is a hunter that barely moves, that lacks eyes, jaws, or speed, yet succeeds through chemistry, patience, and a feeding strategy that bypasses conventional defenses. It reminds us that danger in the ocean is not always fast, visible, or dramatic. Sometimes it approaches at the pace of certainty, guided by invisible trails and a method that does not require a fight. The final realization lingers uncomfortably. In the ocean, you do not need to be chased to be hunted. You can be located without being seen, consumed without being bitten, and defeated without realizing when the encounter truly began. The starfish embodies this truth perfectly, an understated nightmare of the sea floor that proves survival is not always about escaping the swiftest predator, but about avoiding the one that never stops moving toward you.